Look up with me for a moment, not with the urgency of a scientist chasing data, but with the patience of someone listening for the quietest sound in the room. The moon hangs there pale and untroubled, and every night it seems to wear the same expression. The same familiar seas, the same battered craters, the same soft unblinking gaze. For all of human memory, it has never turned its other cheek. We sketch its face on pottery and flags, we give names to the shadows, as if they were freckles on a friend, and we tell ourselves a simple story: the moon does not spin. But stillness in the sky is often a costume worn by motion. The moon is not a statue, it is a dancer who never breaks eye contact with her partner. So, before we continue, hit like and subscribe so you don't miss a single revelation as this story unfolds moment by moment in real time. Tell me in the comments where you're watching, from what time it is there, and whether you believe we're hearing the whole truth about what's unfolding above our heads. And if you want to keep the signal alive, share this video on X, Facebook, Reddit, or even just with the people who still look up at night. You are the reason we can keep following the impossible, and for that, thank you. The paradox begins with a rhythm so precise it hides inside plain sight. In roughly 27.3 days, the moon completes a journey around Earth. In exactly that same span, it also completes one slow rotation about its own axis. One orbit, one spin, locked in step. This is why one hemisphere, what we call the near side, faces us always, and the far side remains out of view. If you could hover above the North Pole of space and watch the pair from afar, you would see the moon turning elegantly just fast enough to keep the same face toward Earth. What looks like a refusal to move is in truth perfect choreography, a spin matched to an orbit so exactly that the two cancel in our perspective. There is a simple way to feel this even without equations. Hold a coin between your fingers and move it in a circle around your head, keeping one side of the coin always facing your eyes. Notice how your wrist must rotate the coin as it goes. That on a grander and quieter scale is what the moon does. It turns once per trip. The illusion comes from our vantage point. Our lives are lived on the stage, not in the balcony. Behind this graces gravity, an artist with a patient hand. Long ago the moon likely spun fast, a young ember thrown from a turbulent early Earth days whipping by in hours, but Earth's gravity tugged at it unevenly, raising slight bulges in the moon's body rock, not water, but still obedient to pull. Because the moon was rotating, those bulges lagged a little behind the line connecting Earth and moon, and that misalignment acted like a brake. Inside the moon, friction warmed stone, and over unfathomable time, some of the moon's rotational energy bled away as heat. Rotation slowed, orbit continued, and slowly, like a pendulum losing swing, the moon settled into a rhythm where one spin equals one circuit. Tidal locking scientists call it nature's way of achieving stability through the loss of motion. We live amid evidence of this everywhere we look. The near side's great dark plains, the Murraya basalt frozen from ancient flows, mirror a past when the moon's interior was warmer and more yielding to the pull, while the far side, thicker crusted, wears the older scars of impact largely untouched. The moon's very shape is a memory of that long conversation with gravity, a slightly stretched, slightly asymmetrical world, tuned until the talk quieted and the bulges lined up and the breaking ceased. From then on, the face we know was chosen not by poetry but by physics. The quiet perfection of the lock is not unique, which is itself a wonder. Walk the solar system in your mind and you'll find other companions with the same composure: Jupiter's Io and Europa Saturn's Titan, even distant Pluto dancing with Charon, each keeping one side turned toward its partner. The recipe is the same, the relentless patience of tides, but Earth's moon is special to us because of its scale and intimacy. It is large for a satellite, close for a neighbour, bright enough to govern tides, lengthen days, and steady the tilt of our planet, so that seasons arrive with a predictability life could learn to trust. And yet, even in this hush, there is motion you can't see on a single night. The moon breathes in small ways. Libration astronomers say a gentle rocking that lets us glimpse a little beyond the limb, a slow nod toward one pole, and then the other, a subtle side-to-side sway, born of an orbit that is not a perfect circle, and a spin that keeps perfect time on average. Over weeks, the face we think we know reveals a little more than half its skin, about 59% in total, like a confidant who occasionally turns just enough to show another scar. Motion everywhere hiding inside the word still. To say that the moon spins is to say more than a fact. It is to accept that our senses specialize in the near now, while the universe prefers the long slow. We're tuned to minutes and days. The moon is tuned to months and eons. What seems frozen to us is simply moving at a tempo too patient for our urgency. In that mismatch lies the first invitation of this story to slow down, to let the clock of gravity set the pace, to notice that silence is not absence, but balance. If you need numbers to anchor the feeling, the arithmetic is straightforward and humbling. A single turn in 27.3 days is a rotation rate of roughly 1 revolution per month, an angular whisper compared with the spinning Earth beneath your feet. The Moon's orbital path carries it around us at about 1 kilometre per second. Its rotation ensures that as it travels it constantly reorients just enough to keep facing home. Each night is a different point on a circle, each night the same face returned like a lighthouse that never looks away. What waits ahead in this journey is the invisible machinery that makes such a rhythm inevitable. Threads of gravity stretched across space energy, traded and dissipated like warm breath on cold glass, a ledger of angular momentum balanced over billions of years. You will meet the cosmic break that transformed a wild young world into a careful partner. You will visit the hidden hemisphere first, revealed by a humming Soviet probe. You will feel the faint outward drift centimeters per year that proves the conversation between Earth and Moon is ongoing even now. And because wonder likes its edges, you will glimpse what would happen if that lock ever slipped, how tides would stagger and seasons lose their metronome, and why thankfully gravity is a stubborn sculptor that prefers its statues stable. For tonight, let the paradox breathe. The Moon seems not to turn, and yet it turns with exquisite fidelity. It appears to keep still, and yet it is the outcome of motion spent and motion sustained. It looks simple, and yet it is the visible surface of a deep equation written in a rock and light. The face above you is not a refusal to move, it is the promise of a promise kept, a dancer in a long waltz, a companion who learned through patience and pull to keep looking back. If this calm feels like sleep coming on, let it. The science will be here when your attention returns unchanged and unhurried. In the next part, we will step behind the illusion and watch gravity at work the way a clockmaker opens a casing to show the gears. We will trace the threads that tug the bulges, that lag the heat, that fades, and we will see how the universe over enough time exchanges speed for certainty and spin for harmony. For now, hold the picture. One orbit, one turn, one face forever, turned toward home. The Moon is moving. The Moon is spinning. The Moon is still. All three can be true at once if you listen at the right speed. Imagine for a moment that the universe could play music. If it did, the Earth and Moon would be a duet, slow, deliberate, and perfectly timed. Each note, a revolution, each pause, a turn. One world spins fast, wrapped in blue oceans and air. The other turns slowly cold and grey, keeping its gaze locked on the first as if afraid to look away. This is synchronous rotation. One rotation per orbit, a balance so exact that it feels less like mechanics and more like choreography, written in gravity's invisible ink. Every 27.3 days, the Moon completes this exquisite cycle, spinning once on its axis, while orbiting Earth once around. To us, that precision erases movement. We see only the same face, the same seas of tranquility, the same dark scars of lava plains. But from the Moon's point of view, the dance never ends. Each point on its surface feels the pull of Earth shifting across the sky, slow and constant. The Earth never rises or sets there, it hovers motionless, always in the same spot, blazing blue and white over the lunar horizon. To stand on the Moon's near side is to live beneath an eternal Earth. To stand on its far side is to know the opposite, an eternal absence. This synchrony is not magic, it is physics expressed as patience. The Moon's spin and orbit have settled into resonance, a ratio of 1 to 1, where the centrifugal tendencies of rotation and the gravitational pull of Earth cancel perfectly. The angular velocity of its spin equals the angular velocity of its orbital motion. At that point, tidal torques, the twisting forces that once acted as brakes, disappear. The system no longer wastes energy fighting itself. It becomes efficient, stable, timeless. And yet in this perfection lies a hidden fragility. A millimetre too fast, a second too slow, and gravity would begin its correction again. The forces between Earth and Moon are constantly whispering, adjusting, refining the balance by imperceptible degrees. It's a relationship of exquisite feedback, self-healing, self-stabilizing, but never quite static. Every tide that sweeps our shores, every centimetre of the Moon's outward drift is part of that ongoing conversation. Astronomers call this state synchronous rotation, but poets have always known it by other names. The ancients looked up and saw constancy in an uncertain world. To the early Sumerians, the moon's steady face was the eye of Nana, the god who watched over the night. The Greeks imagined Selene driving her chariot across the same path, each month unchanging, serene. In China, the moon was Chang'e's lantern glowing eternally over the same silent palace. Long before we understood orbital mechanics, we sensed its rhythm. Across cultures, across millennia, people measured time by its motion and comforted themselves with its stillness. To know that the moon kept the same face was to believe that something, at least in the heavens, could be trusted. The irony is that this very stillness is a product of change. Early in its life, the moon spun fast, perhaps one rotation every few hours, while Earth's tides clawed at it, slowing its spin. The process took tens of millions of years, but it ended in harmony. In that time, the moon shed enormous amounts of energy heat bleeding from its interior until it cooled, solidified, and found its quiet rhythm. That final alignment, once reached, is extraordinarily precise. NASA's laser reflectors placed on the lunar surface by Apollo astronauts show that the moon's orientation toward Earth wobbles by only a few arcseconds, fractions of a degree over centuries. It is by all practical standards perfect, and this perfection is not unique to us. Throughout the solar system, gravity performs the same long, slow act of synchronization. Jupiter's moon, Io, constantly squeezed and stretched by its planet's immense pull, keeps one hemisphere forever lit by Jupiter's storms. Europa, beneath its crust of ice, does the same. So do Ganymede, Titan, Rhea, and dozens more. Even Pluto and its companion Charon are locked together in a double embrace, each showing the same face to the other, orbiting a shared center of mass that lies outside both bodies. The universe, it seems, has a taste for symmetry. But among all these pairs, Earth and Moon stand apart. The ratio of their sizes is unusually intimate. The Moon is over a quarter of the Earth's diameter, and more than 1% of its mass, enormous by cosmic standards. This closeness gives their relationship a strength and sensitivity no other planet-moon pair quite matches. It's why our tides are powerful enough to sculpt coastlines, why our days slowly lengthen, why Earth's axis holds steady instead of wobbling wildly. Without the moon's measured pull, the rhythm of life itself would drift. That idea that stability comes from surrender, that energy spent leads to peace, is perhaps the quietest moral of the moon's motion. We see a world that has given up its freedom to spin in exchange for eternal balance. It could be said the moon learned stillness the way a dancer learns discipline through repetition, until the motion becomes invisible. Imagine standing at the rim of Mare Serenitatis, watching Earth hang above the horizon like a living moon. You would see the oceans shimmer, storms swirl. Continents drift in sunlight and shadow, all from one unchanging spot in your sky. You would never see sunrise or sunset. The light would brighten and dim over the course of a month as Earth's own phases waxed and waned. But the position would never move. The concept of day would lose its meaning. Time itself would become the motion of Earth's colors shifting through blue and white and gold. Synchronous rotation creates worlds of eternal perspectives. On one side, endless day, on the other, endless night. For the moon, it is equilibrium. For us, it is poetry. Even now, the mathematical precision of this dance echoes through the language we use to describe it. Month comes from moon, our calendars, our tides, our folklore. Each is a relic of this relationship, proof that our species learned to count and to hope by watching a celestial partner that never turned away. So when we call the moon's motion perfect, we mean something larger than numbers. We mean a kind of agreement between matter and force, between chaos and calm. It's the universe showing what happens when gravity has time to work through its arguments and find compromise. The moon is the result of that cosmic diplomacy, a world that spins and circles at the same pace, every action mirrored by its orbit, every revolution a return to the same view. In the next part, we'll open that perfection and examine its machinery, the hidden torque, the internal friction, the subtle stretching that first slowed the moon and still keeps the lock today. You'll see that beneath this graceful balance is a story of invisible labor energy, lost crust bent, and gravity's unending patience. But before we look inside the engine, hold this thought. What we call stillness is often just motion balanced so finely that our eyes can't tell the difference. The moon's face is proof. If you could peel back the night and see gravity itself, the invisible tension lines binding Earth and Moon, you would find a web of threads, countless and silent pulling in perfect equilibrium. Each thread is a vector of force, each vibration a transfer of energy, and though we cannot see them, their effects are written everywhere in the shape of the tides, the rhythm of our days, and the moon's unwavering gaze. These are the threads of invisible force that have tied two worlds together for 4.5 billion years. The story begins with a deceptively simple idea, one that changed the way we understand motion, Newton's law of universal gravitation. Every mass in the universe attracts every other mass. The strength of that attraction depends on how massive the bodies are and how far apart they sit. The formula F, G m-mos om m2 or r2 is simple enough to fit on a chalkboard, yet vast enough to govern galaxies. Here G is the gravitational constant m1 and m2 are the masses of Earth and Moon, and r is the distance between them. The smaller r becomes the stronger the pull, but this law elegant and still hides an untidy truth: celestial bodies are not rigid spheres. They bend, they yield, they respond. When Earth pulls on the moon does not remain perfectly round. Its rock under stress stretches ever so slightly. Imagine a soft rubber ball being tugged at one side, two tiny bulges form, one facing the source of the pull, the other opposite it. These are tidal bulges raised not by oceans but by gravity itself. Now imagine the moon spinning. Because it rotates, those bulges cannot stay perfectly aligned with the line connecting Earth and Moon. They lag a little behind, like fabric twisting under tension. That offset is the key. In that small misalignment, physics finds leverage. The gravitational pull from Earth on the displaced bulges produces a torque, a twisting force that acts against the moon's rotation. Over millions of years, that torque acts like a brake, extracting angular momentum from the moon's spin and converting it into heat. The faster the moon rotates, the stronger the misalignment, and the more heat is generated inside its crust and mantle. It's a self-correcting mechanism. The more the moon fights the pull, the more it slows. Scientists call this process tidal friction, but to imagine it, think of a heavy wheel submerged in honey. Every time the wheel turns, the honey drags against it, converting kinetic energy into warmth. The wheel eventually stops, not because the honey resists it absolutely, but because the system is constantly transforming motion into heat, until equilibrium is reached. In the moon's case, the honey is its own rock, deforming microscopically, shifting, flexing and generating internal friction that once kept parts of its interior molten. To see this with numbers, billions of years ago, when the moon's rotation was fast, the tidal torque acting upon it may have reached 1016 Newton meters of force powerful enough to heat rock hundreds of kilometers deep. That warmth, long since dissipated into space, once left fingerprints on the moon's surface. NASA's GRAIL mission, the Gravity Recovery and Interior Laboratory, launched in 2011, mapped the moon's gravitational field with unprecedented precision. What it found confirmed the theory: subtle variations in density across the crust regions of thinning and thickening patterns that match predictions from tidal deformation models. Even now, the moon's shape is slightly elongated along the Earth-Moon line, its very geometry a fossilized record of strain. JAXA's Kaguya-Selene orbiter circling the moon from 2007 to 2009 added another layer of evidence. Its laser altimeter and spectral imagers detected not only topographic asymmetries, but also variations in heat flow that align with the same ancient stress fields. These data show that billions of years ago, the moon's internal structure flexed under Earth's pull like a colossal breathing lung of stone. Each breath, each tiny deformation cost energy. Each breath slowed the spin. This is the essence of the cosmic break. It doesn't grind or screech, it whispers. The energy of rotation is siphoned off and redistributed. Some of it leaves as heat through the crust. Some of it migrates into the orbital motion, pushing the moon slightly farther away even as it slows. The system behaves like a figure skater who extends her arms to slow her spin. Momentum conserved, motion transformed. Nothing is lost, it merely changes form. The mathematics behind this are old, but the picture remains elegant. Johannes Kepler first described how planets move not in perfect circles, but in ellipses, their speeds changing as they near or recede from the sun. Newton later gave those curves a reason: the mutual pull of gravity. Together, their insights describe the dialogue between orbit and rotation. The moon's lock is one outcome of that dialogue, where forces once in opposition have settled into a rhythm so stable that it feels like silence. And yet this silence is dynamic. Even today, measurements show that the Earth-Moon system continues to evolve. Laser reflectors placed by Apollo missions and later by Lunar rovers reveal that the Moon drifts away at about 3.8 centimeters per year. This is the faint echo of that same tidal torque, still at work, not enough to alter the lock, but enough to keep the system alive. Earth's gravity pulls on the Moon, raising those ancient bulges anew, while the Moon tugs back on Earth's oceans, lengthening our days by milliseconds per century. The cosmic break, though almost spent, never fully stops. It's strange to think that the Moon's perfect stillness was purchased with heat and motion. Somewhere in that long cooling, the molten plains we call Maria were born lava seas that filled giant basins on the near side. After impacts opened fractures deep into the mantle. The far side, thicker and less yielding, cooled differently, preserving its rugged highlands. Even the asymmetry of the lunar crust is testimony to the slow breaking of time. One hemisphere softened and reshaped. By tidal heating, the other hardened in perpetual shadow. Dr. Maria Zuber, principal investigator of NASA's Grail mission, once said, "The Moon's gravity field is a fossil. It remembers everything. The asymmetry, the density variations, the long scars beneath the surface, all are memories of when the Moon was still fighting its leash, still spinning against the invisible threads that now hold it steady. Those threads woven of force and friction stretched but did not break. Over billions of years they pulled the Moon into step with Earth until the tug-of-war became a waltz. If gravity is the sculptor of the cosmos, then tidal friction is its chisel-carving motion into form, shaping chaos into balance. We owe the Moon's quiet to the same violence that once nearly tore it apart, and that perhaps is gravity's greatest artistry. It achieves peace not by gentleness but by persistence." In the next part, we will follow the energy that vanished into warmth, the heat that once glowed beneath the Moon's crust, and see how that hidden fire transformed into harmony. We'll measure what was lost, what was gained, and how in the ledger of the cosmos, every slowing spin buys the music of balance. For now, let the picture settle in your mind, two worlds bound by invisible threads, one pulling, one yielding, and between them the faint sound of motion turning into stillness, the quiet hum of the cosmic break. In space there are no breaks, only resistance disguised as time. The Moon's slow surrender to Earth's gravity was not a collision, not even a struggle, but an act of endurance measured in aeons. What began as wild rotation, one spin every few hours, became a near motionless turn lasting 27 days. To lose that speed required something enormous, the steady bleeding away of rotational energy, converted into heat, stone stress, and permanent change. Physicists estimate that during its long descent into synchrony, the Moon dissipated roughly 1019 to 1020 joules of energy. It's a number so large it resists imagination, yet it can be compared enough heat to power every human civilization at today's consumption for millions of years. All that energy once lived in the Moon's spin. None of it vanished. It went inward, warming rock, melting mantle, deforming crust, and outward in the form of an orbit that slowly expanded. The Moon traded rotation for distance fire for balance. NASA's Grail mission mapped the fingerprints of that transformation. Twin spacecraft flying in formation only a few hundred kilometers above the lunar surface measured minute changes in gravitational pull as they passed over mountains, basins, and buried mass concentrations. From those variations, scientists reconstructed the Moon's internal density with a precision once thought impossible. The result was a gravitational relief map, a portrait of strain frozen in stone. Beneath the Maria, vast networks of fractures and density anomalies mark where tidal heating once flowed. These regions align almost perfectly with simulations of how tidal stress would have propagated through a young, partially molten Moon, locked in its long, breaking spiral. What Grail revealed was not a uniform world, but a world with memory-lighter crust, where heat once softened rock, heavier concentrations where the lithosphere resisted. The Moon's center of mass sits about 1.8 kilometers closer to Earth than its geometric center, a subtle but lasting offset created by this differential heating. It is as if the entire body leaned forward during its final deceleration and never straightened again. Geologists studying returned Apollo samples find further proof. The basaltic plains of the near side are rich in elements like thorium and potassium radioactive materials that produce internal heat. Their concentration suggests that tidal friction and radioactive decay work together turning the moon's early interior into a convecting cauldron. Over time, as the moon's spin slowed, this internal energy escaped, the crust thickened unevenly, and the molten heart stilled. The far side, deprived of both tidal stress and heat, froze first. What we call the dark side is literally the colder half of a planet that cooled asymmetrically tilted forever toward its source of warmth. JAXA's Kaguya orbiter confirmed that ancient deformation isn't just visible from space, it is measurable in the terrain. Subtle ridges and wrinkle faults trace lines of compression, caused when the moon's once heated interior contracted as it cooled. The landscape itself bears the geometry of exhaustion. To think of this in human terms, imagine spinning a heavy potter's wheel and slowly pressing your hands against the clay until friction warms it. The wheel slows, the clay stiffens, the heat fades, leaving only shape. The moon's story is that process written across billions of years and 1,000 craters. It is the artistry of slowing down until motion becomes form. Scientists call this transition tidal damping, a phrase that sounds sterile, but behind it lies one of nature's most graceful exchanges. Rotational energy became thermal energy. Thermal energy escaped into space. Mechanical stress reshaped rock, and what remained was equilibrium. In purely thermodynamic terms, the system lost usable energy. Entropy increased, but what humanity gained was harmony. The same law that dims a spinning top to rest gave us the steady tides that cradle Earth's coasts, the stable tilt that keeps our seasons gentle, and the silver clock that measures months with unerring calm. Perhaps this is what nature means by stability, not absence of change, but change brought to rest. Every system seeks a state where energy can no longer flow freely, where tension resolves, where the contest between motion and resistance finds silence. For the Earth-Moon pair, that silence is tidal locking. The torque ceased, the crust cooled, the fractures sealed. The dance slowed to a heartbeat, one beat per orbit, one turn per month. If we could have stood above it as it happened, an impossible observation, but imagine we would have seen a world glowing from within heat lines, shimmering through basaltic plains, the surface flexing as gravity kneaded it like dough. Over millions of orbits the glow would dim, the shape would stabilize, the vibrations would fade, until at last the moon's rotation and orbit merged into one breathless rhythm and the world fell quiet. Dr. James O'Donoghue of JAXA once described this balance as nature's patience made visible. That phrase fits. The moon's calm is not the peace of still water, but of water that has been flowing long enough to carve stone smooth. To watch it now gleaming above the clouds is to see entropy turned into elegance, a record of motion spent wisely. In a universe where energy must always run downhill, the moon shows what can be built along the way, mountains, patterns, order. The heat it lost became the symmetry we see. The friction that slowed it gave us time itself, the lunar month, the tides, the soft light that governed agriculture, ritual and rest since the first humans looked up. Energy lost, harmony gained. That is the quiet arithmetic of the cosmos. In the next part, we'll look at how that exchange continues even today, how every tide on Earth still transfers a trace of energy back into the sky, nudging the moon farther away and reminding us that balance once achieved is not the end of motion, but its gentlest form. The moon looks eternal in its place, a patient witness above the clouds, but it is leaving us. Quietly and visibly, centimetre by centimetre, our oldest companion drifts away at a rate of 3.8 centimetres per year, about the width of a fingernail each month. It's a pace too small for eyes to notice, and yet vast enough to reshape the clockwork of the Earth-Moon system over time. The universe rarely says goodbye in haste. It prefers the slow farewell of gravity undone. We know this distance not from guesswork, but from light itself. In 1969, the Apollo 11 astronauts placed a small glassy device on the lunar surface, the Lunar Laser Ranging Retroreflector, a grid of corner-shaped mirrors designed to bounce light directly back to its source. When scientists on Earth fire a laser pulse at it, the beam travels 384,400 kilometers to the moon, touches those mirrors, and returns 2.5 seconds later. The round-trip time tells us the distance with exquisite precision within a few millimeters. Each year the delay grows slightly longer. The data are unambiguous. The moon is receding. But why? Because the same tidal friction that once slowed the moon still works on Earth. The pull of the moon lifts two great bulges in our oceans, one facing the moon, one on the far side. If Earth and Moon were motionless, these bulges would align perfectly along the line between them. Yet Earth rotates once every 24 hours, much faster than the Moon's month-long orbit. As a result, the oceanic bulges are dragged a little ahead of the Moon's position, tilted forward like waves outrunning their tide. That slight offset is everything. The mass of those displaced waters tugs gravitationally on the Moon, giving it a tiny forward pull in its orbit. A forward pull means extra energy. The Moon climbs to a higher, slower orbit just as a satellite would if you fired its engines briefly along its path. At the same time that interaction exerts an equal and opposite torque on Earth itself, robbing our planet of rotational energy. The day lengthens by a few milliseconds every century. It is the gentlest of exchanges, our spin for the Moon's distance. NASA's Apollo, the French Lunar Laser Ranging Experiment, and later the Apache Point Observatory, Lunar Laser Ranging Operation Apollo in New Mexico, continue to measure this drift with astonishing fidelity. What they see confirms Newton's ancient equations and adds nuance to them. The Earth-Moon system behaves like two dancers bound by a taut ribbon, one whirling fast, the other slower. With each turn, energy slips down the ribbon, and the spacing between them widens. It's a transfer so constant that scientists now model the entire Earth's interior atmosphere and oceans as part of this gravitational coupling. The Moon pulls the seas pull back on the Moon. The friction of water on the seafloor becomes a cosmic engine. That engine is not small. Tidal friction dissipates about 3.7 terawatts of power, nearly the same as humanity's entire global energy use. Most of that power becomes heat in the oceans, but a fraction becomes motion in the Moon's orbit. Over eons, that whisper of thrust has added tens of thousands of kilometers to the Earth-Moon distance. When the first trilobites crawled in Cambrian seas 500 million years ago, the Moon hung roughly 20,000 kilometers, closer than it does now, and loomed larger in the sky. Back then, a day lasted about 21 hours, and there were 420 days in a year. The fossil record itself confirms this tidal rhythmites. Ancient sedimentary layers deposited by rising and falling seas preserve daily and monthly cycles that match the predictions of this drift. The conversation between Earth and Moon is written in stone. Dr. James O'Donoghue of JAXA calls it a gravitational handshake that never ends. Each side gives a little, receives a little. The Moon gains altitude. Earth loses momentum. Both remain bound in the same dance. It's easy to think of gravity as a one-way force, a pull, but here it behaves more like a dialogue. Earth's oceans speak first, their tides tugging, their friction humming. The Moon answers with distance translating energy into space. And though this widening might sound like separation, it is in truth the reason the partnership endures. Without the outward drift, the two bodies would spiral toward collapse, their energies unchecked. Instead, the friction acts as a stabilizer, slowing both until they find mutual rhythm. It is not a breakup, it's a balancing act. Think of it as an old couple walking hand in hand across a vast plain, slowing their pace together as they age. Each step takes them fractionally farther apart, but the bond remains connected by the quiet thread of gravity. If you could stand on the Moon and watch Earth's rotation slow over geological time, you would see the continents turn ever more languidly beneath the same shining seas. The tides would weaken, the days stretch longer. From Earth, the Moon would drift imperceptibly outward, its orbital period lengthening in sympathy, always staying in tune. This, then, is how the universe speaks in patience. Every wave that rolls ashore, every tide that rises beneath a harbor's pilings, every millisecond added to the length of our day is part of that same slow conversation. Gravity asks for equilibrium, friction translates, time records the minutes. Together they compose a language that needs no sound. The Moon may one day settle into complete mutual lock with Earth, both showing the same face forever, but for now we live in the middle of the sentence, in the pause between question and reply. The beam of light that leaves a telescope in New Mexico touches the lunar mirror and returns to our waiting eyes is not just an experiment in physics. It is a message traveling across 384,000 kilometers of shared history, a pulse of light echoing between two bodies that have been speaking in gravity for billions of years. A whisper that says simply, "I'm still here." And in the next part, we'll explore what that conversation tells us about the future, how the same friction that steadies the Moon's path shapes the fate of Earth itself, and why every tide is both a reminder and a rehearsal of the cosmic balance yet to come. 4.5 billion years ago, the Moon was not the pale serene witness. We know it was chaos itself, a glowing ember torn from the wounds of Earth. The newborn solar system was a violent sea of collisions, molten worlds and orbits that hadn't yet decided where to rest. Out of that chaos came an impact so immense that it nearly erased the young Earth, and yet from the wreckage built the companion that now steadies our nights. Scientists call it the Theia collision, but it was less an event than a cosmic baptism of fire. Imagine a protoplanet Theia roughly the size of Mars strikes Earth at a shallow angle, travelling at 9 kilometers per second. The energy released is beyond comprehension, enough to melt both worlds and fling vaporized rock into orbit. For a brief time, Earth is surrounded by a halo of incandescent debris glowing like a second sun. Inside that halo, fragments of molten stone gather and merge, cooling and compacting under gravity's insistence. Within weeks, or perhaps months, a sphere begins to form, our moon, still glowing red, with heat surface temperatures above 2000 degrees Celsius. If you could have stood nearby, an impossible act in a time before air, you would have seen a world wrapped in magma. Rivers of molten silicate flowed across its surface. Geysers of vaporized minerals burst skyward in plumes of gold and crimson. The newborn moon was spinning rapidly, completing one rotation in just a few hours. Its glow would have been visible from every corner of the molten Earth, a fiery mirror circling its parent like a ghost of the impact that birthed it. The night sky, if it could be called, that would have been filled not with stars but with incandescent ash. Earth too bore its scars. The collision left it larger faster and tilted a spin that turned in less than 10 hours per rotation. The tides raised in its molten seas by the newborn moon would have towered hundreds of meters high, dragging oceans of lava across its surface. Each tide was a transfer of energy, a hammer and chisel shaping both worlds. Gravity, the patient sculptor, had begun its slow work. As the moon cooled, it faced a new kind of battle, not with impacts or heat, but with friction. Earth's gravity pulled hard on the still fluid moon, raising immense tidal bulges in its molten mantle. Because the moon was spinning faster than it orbited, those bulges lagged behind, and that lag produced torque, a twisting force that acted as a cosmic brake. With each rotation, energy drained from its spin and seeped into its interior as heat. You could say the moon began to burn itself calm. NASA's simulation suggests that in those early centuries the moon's surface radiated with a steady volcanic glow. The heat generated by tidal friction was comparable to the power output of millions of erupting volcanoes. Waves of molten rock surged beneath a crust that had barely begun to form. On Earth, the pull of the moon's gravity slowed our planet's rotation ever so slightly, lengthening the day by fractions of a second, while the moon itself inched outward, an invisible negotiation that continues even now. Over millions of years, the molten moon began to harden. Its crust thickened like cooling glass, cracking and folding as tides flexed it from within. Tidal heating sculpted enormous basins and fissures that later filled with lava the seas of basalt we call Maria today. These dark plains, the seas of tranquility, of serenity, of rain, are frozen remnants of that slow-breaking process, the scars of motion tamed. The far side, thicker and less exposed to Earth's heat, solidified earlier and kept its rugged complexion a record of the first asymmetry ever written between the two worlds. If we could watch this transformation in time-lapse, billions of years condensed into minutes, we would see the moon's spin decelerate with heartbreaking grace. The fiery world turns faster than we can blink, then slower, the glow fading from orange to ash-grey. Each frame would show less movement, fewer eruptions, the crust cooling the magma seas, retreating into silence. Until finally, the moon would complete one rotation per orbit, the last flicker of heat giving way to the first reflection of sunlight. Stillness achieved through surrender. The process was not instantaneous, it may have taken tens of millions of years, but time in planetary terms is generous. Tidal friction, though invisible, is relentless. Even as the moon's outer shell cooled, its core likely stayed warm for eons, reshaped by the steady kneading of Earth's gravitational pull. Modern data from NASA's Grail mission and Japan's Kaguya orbiter show that deep inside the moon still carries traces of this internal deformation, density variations, fossilized stress lines, and uneven crust thickness that match models of ancient tidal heating. The moon quite literally remembers the pain of its making, and Earth too remembers. The same gravitational handshake that slowed the moon, stabilized our own tilt, fixed our seasons, and set the tides in motion. The waves that crash on today's shores are echoes of that first, molten tide, gentler now, but born of the same exchange. The moon's breaking turned chaos into order, fire into rhythm. There's something almost tender in that physics. Two bodies forged in violence finding stability not by force but by loss. Every joule of energy that left the moon's spin became a step towards serenity. Its rotation slowed, its orbit widened, it cooled, it quieted. The wild child of collision became the measured guardian of Earth's tides. If you could stand on its surface today and look back, you would see the planet that gave it both birth and restraint. The blue world would hang unmoving in the lunar sky, immense and luminous, whispering its gravity across the void. The moon would answer not with sound, but with stillness, a stillness earned by 1 billion years of slowing down. From that calm our nights were born. From that fiery dance came a balance so perfect we mistake it for peace. The moon was once wild, spinning and burning in the afterglow of catastrophe. Now it is a mirror of that event's resolution, a world that turned its violence into grace. In the next part we'll look closer at the scars left behind by that transformation, how the moon's frozen crust, uneven and fractured, still holds the memory of motion, the silent geometry of a world learning how to stop. When the last of the magma oceans cooled and the furious tides subsided, the moon began to wear its history on its skin. Every ridge basin and buried fault line became a page in its autobiography, a chronicle of motion written in stone. What we see tonight, that pale, scarred disk, is not merely a cratered world. It is a fossilized record of a celestial body remembering how to slow down. As the moon's surface hardened, it locked in the tension that had once flowed like heat through its molten interior. The crust, roughly 50 kilometers thick on average, did not form evenly. On the near side, the face turned toward Earth lava continued to well up through fractures, opened by tidal flexing. On the far side, the crust cooled faster and thicker, sealed against that gravitational heat. This imbalance became permanent, the near side smoother and darker, the far side rough and bright. That asymmetry is not coincidence, it is the physical memory of motion arrested. Scientists call it the near-far dichotomy, one of the great puzzles of planetary science. Why should one hemisphere bear seas of basalt and the other highlands of ancient crust? The answer emerging from missions like Smart 1 and Grail lies in the moon's turbulent youth, when its rotation was slowing and tidal forces were strongest. The European Space Agency's Smart 1 orbiter, launched in 2003, used its electric ion engine to spiral around the moon, mapping mineral distributions with infrared and X-ray spectrometers. Its findings reveal that the near side is unusually rich in potassium K rare earth elements, REE, and phosphorus P, collectively known as K-REAP. These are the residues of the last molten layers to crystallize in the lunar magma ocean. They carry heat-producing isotopes such as uranium and thorium. In short, the near side had the ingredients to stay warmer longer. Why did those elements pool? Their Grail's gravitational mapping later provided the missing clue. The twin spacecraft showed that the moon's center of mass is offset toward Earth by nearly 2 kilometers, and the crust on the far side is on average 15-20 kilometers thicker. This asymmetry likely formed when tidal forces and Earth's radiated heat worked together on a still soft moon. As the young moon rotated faster than it orbited, the constant stretching and squeezing generated internal friction. The side facing Earth remained hotter, more pliable. The far side cooled and solidified early. When rotation slowed to match orbit, that imbalance froze in place. The near side surface, unable to support its own weight on a thinner crust, sagged into basins later filled by basaltic flows to form the Maria. The far side, rigid and thick, kept its craters sharp and its highlands lofty. The Lunar Reconnaissance Orbiter and Kaguya later confirmed this pattern. Enormous basins, like Imbrium and Serenitatis, are not random impacts, but occur where crustal thinning was greatest direct consequences of ancient tidal heating. The moon's geography, in other words, is a map of stress relieved. The fractures trace where gravity needed the world most deeply. If you were to hold a model of the moon in your hands and run your fingers across its surface, you could feel this story. One hemisphere is slightly flattened, elongated toward Earth by about 2,000 meters. That distortion is the fossilized shape of a world once spinning too fast, caught in the act of slowing. The torque that once twisted its body is gone, but its geometry remains tilted permanently, leaning toward its partner in orbit. Even the subtle bulge locked under the Maria is part of this memory, the leftover of tides that turned to stone. Planetary scientists sometimes call this fossil tidal bulge the moon's frozen tide. It is as if a wave were caught mid-crest and petrified, suspended forever. In that silent relief, we can still read direction pressure and the rhythm of the past. The moon remembers not just that it moved, but how it moved, how it twisted and strained until friction stole its spin. When ESA's Smart 1 sent its final images back in 2006, before deliberately crashing into the Lake of Excellence, its cameras caught a haunting view, the smooth basalt plains of the near side melting into the rugged terrain of the far. The contrast is stark, like two halves of a single-thought, restless youth beside settled age. The spacecraft's sensors detected the lingering trace of thorium in the Maria, an echo of the moon's warm heart still glowing faintly beneath the surface. Even in death, the probe confirmed the truth. The moon's face and far side are not opposites, but stages of one evolution motion cooling into memory. In geological terms, this memory is everywhere. The wrinkle ridges, sinuous rills, and concentric rings of basins such as Imbrium and Oriental are all evidence of contraction after internal heat drained away. The crust shrank, buckled, folded on itself like drying clay. Those wrinkles are time made visible, the skin of a planet tightening as it ages. The far side, meanwhile, preserves the scars of impacts untouched by lava. Its brightness comes from anorthosite crystals of plagioclase that floated to the top of the lunar magma ocean and froze. To look upon that surface is to look back to the first 100 million years after the solar system formed, when craters rained like meteoric hail, and the moon, still pliant, recorded every strike. The far side's silence is not emptiness, it is preservation. Scientists sometimes speak of planetary memory as a metaphor, but in the moon's case it is literal. Every crater, every density anomaly, every offset in its center of mass carries the imprint of its relationship with Earth. The two are inseparable. Without the Earth's tidal hand, the moon's asymmetry would never have formed. Without the moon's yielding, Earth's rotation would be swifter, its days shorter, its axis less stable. The scars of one are the balance of the other. There's a strange tenderness in the idea of a world remembering its motion. The moon no longer spins freely, yet it carries the handwriting of that long surrender. It has no atmosphere, no erosion, nothing to blur the record. Its silence is archival. When we look up, we see not just a satellite, but a diary entries written in the language of basalt and time preserved for billions of years by the absence of change. In the deep vacuum of the lunar night that stillness hums, it's as if the moon whispers through its geography, I have moved, I have turned, I have cooled, I remember. And in that remembrance lies the beauty of all things that slow down, the way motion leaves its trace, not in what continues, but in what remains. In the next part, we'll travel beyond the face we know to the world. We never see the far side revealed by machines and light, where the silence is deeper and the memories even older. There, the moon's hidden half tells the rest of the story. What happens when motion ends, but history still glows beneath the dust? Until 1959, half of the moon did not exist to us, not truly. For all of human history, poets, sailors, and astronomers had studied that same luminous face, the near side, with its familiar seas and eyes of shadow, but the other half remained legend. It was the unseen, the unreachable, a hemisphere that turned its back forever. Philosophers speculated. Artists imagined jungles or mirror cities. Even serious scientists wondered if a new landscape awaited. And then, in the chill of the Cold War, a small whirring machine broke the oldest mystery of the sky. That October, the Soviet spacecraft Luna 3 rose into the night on a trail of flame from the Baikonur steppe. Barely the size of a refrigerator, its metal skin covered in polished panels, it carried no humans, only film cameras, radio transmitters, and the quiet boldness of a civilization racing its rival toward the unknown. The year before, Sputnik had shocked the world by beeping overhead. Now Luna 3's mission was even more audacious, to swing behind the moon photograph the far side and send the images back to Earth. No one had ever seen that hidden face. 3 days later, on October 7, 1959, Luna 3 crossed the lunar South Pole, entered the darkness, and began to shoot. 18 frames, then another dozen, then more exposed onto strips of photographic film. In a feat of pre-digital ingenuity, the craft developed the film on board with chemical vapor, scanned each image line by line, and transmitted the data by radio back to Earth. The first signals were weak, blurred, noisy like ghosts speaking through static, but what emerged stunned everyone, a completely unfamiliar world. The far side was nothing like the one we knew. Gone were the broad dark plains of the Maria, those basalt seas that made the near side's man in the moon. In their place stretched an almost unbroken wilderness of craters, mountains and light-toned highlands. Fewer than a dozen small mare patches interrupted the rough terrain. One vast circular depression dominated the view, later named the South Pole Aitken Basin, the largest and deepest impact structure known in the solar system, stretching 2,500 kilometers wide and 13 kilometers deep. Here, finally, the moon revealed its dual nature. The near side is thin-crusted, rich in volcanic basalt and heat-producing elements like thorium and uranium. The far side is thick, ancient, and poor in those materials. That difference we now know was forged in its youth. Earth's radiant heat kept the near side warm longer, letting magma rise and flood its basins while the far side cooled early and sealed. But in 1959 these photos were pure revelation. Humanity was looking at terrain no eye, human or animal, had ever seen. The images arrived at the height of the Cold War, and so they were both a scientific breakthrough and a geopolitical signal. Western observers gathered around teletype machines as the first pictures appeared on grainy Soviet prints, white on grey, streaked with static, but unmistakably lunar. Even NASA's scientists amid rivalry felt awe. For the first time, wrote astronomer Gerard Kuiper, we are no longer confined to the familiar hemisphere. The moon has doubled. The public reaction was electric. Newspapers printed the photographs as front-page wonders. The far side of the moon revealed. The world briefly shared astonishment instead of tension. In classrooms, teachers unrolled maps, where one half was detailed, the other blank, and told students that humankind had now seen the invisible. The near side had been a companion for millennia. The far side felt like a secret suddenly confessed. Lunar 3's images were crude by modern standards, resolution measured in kilometers, but they sparked a chain of missions that would redraw our understanding of planetary geology. Later probes. Zond 3 Lunar Orbiter, Apollo 16, Clementine, Smart 1 and Kaguya would confirm what those first photographs hinted. The far side's crust is 20 to 30 kilometers thicker, its density greater, its Maria scarce. Even its chemistry differs lower in iron and titanium, higher in aluminum and magnesium. Where the near side once bubbled and flowed, the far side remained frozen, a relic of the early solar system untouched by volcanic renewal. Standing on that far side, if one could, you would never see Earth. The blue planet would never rise, never set. Its light would never paint the rocks. The stars there are sharp, unfiltered by atmosphere or reflected glow. It is the purest darkness imaginable, a silence so complete that modern astronomers dream of building radio observatories there where Earth's noisy transmissions can't intrude. What began as a mystery of geography has become a sanctuary for listening to the universe. And yet beyond the data, the revelation of 1959 carries a more intimate echo. For the first time we realized that the moon we loved was incomplete in our imagination, that its serenity was a half-truth. Its hidden hemisphere reminded us that beauty can hide complexity, that the familiar often conceals the ancient and the harsh. The moon was no longer a perfect circle of romance. It was a twin-world light and shadow, youth and age, motion and memory. In the midst of the Cold War's race for dominance, Lunar 3 achieved something paradoxically human. It expanded not power, but perspective. Behind the rhetoric of competition, there was wonder, a shared breath of humility before the cosmos. In the grainy grey shapes from a distant machine, we saw proof that mystery still exists, waiting for courage and curiosity to turn it over. Since then, hundreds of probes have followed, each refining the map, but none have recaptured the astonishment of those first ghostly photographs. In them the moon became whole, and so in a small way did we. In the next part we'll journey deeper into that hidden realm, the far side's craters, basins and frozen shadows where sunlight barely touches and silence holds the oldest memories of the solar system. There we'll see how even the darkest face of the moon continues to speak not in light, but in reflection. When Lunar 3's ghostly pictures first arrived, they showed only outlines, a suggestion of peaks and basins blurred through static. 6 decades later, we've walked those shadows in light sharper than dreams. Modern spacecraft have traced every ridge and crater of the moon's hidden, half-turning mystery into map but never robbing it of awe. The far side remains a world apart, without Earth to rise or set its nights last 2 weeks, and its days are blinding. Temperatures swing from 120 degrees in sunlight to 180 degrees in darkness. Where the near side is familiar with our reflected glow, the far side lies in perfect radio silence, a hemisphere of almost sacred quiet. The dust there is older than continents. Its craters, unsoftened by air or water, preserve the solar system's earliest scars. NASA's Lunar Reconnaissance Orbiter, LRO, launched in 2009, finally gave this realm its contours. Its cameras swept over the South Pole Aitken Basin, the colossal wound first glimpsed by Luna 3, a scar 2,500 kilometers wide and deeper than Everest is tall. LRO's laser altimeter mapped the basin's floor in fine relief, revealing concentric rings of uplifted crust and strange patches rich in thorium and other ancient elements. These layers are older than any rock on Earth. In them, scientists read the early solar system's record of bombardment when young worlds were still colliding, and every orbit was perilous. When China's Chang'e 4 mission touched down there in January 2019, it marked a milestone no one else had reached: the first soft landing on the lunar far side. The lander and its small rover U-22 descended into the von Karman crater, a smooth pocket within the Aitken Basin's rough expanse. Because the moon itself blocks direct radio contact with Earth, engineers placed a relay satellite Kuekiao at a gravitational balance point beyond the moon to bounce signals home. That relay is what allows every image and data packet to cross the void, an invisible bridge of communication across absolute silence. The pictures from Chang'e 4 are haunting grey soil strewn with pebbles that may be fragments of the moon's deep mantle ejected by the ancient impact that formed the basin. The rover's instruments confirmed that the far side's crust is thicker, its composition distinct, perhaps containing material from layers never exposed elsewhere. In that dust lies time itself, untouched by wind or rain for over 4 billion years. Scientists studying the samples dream of answers written in isotope ratios. When did the great bombardment end? How long did the lunar dynamo last? Was the young Earth shielded or scarred by its newborn companion? The far side is the perfect archive because it has never been rewritten. Every crater, every glassy bead of fused regolith is a letter in the oldest chapter of planetary history. But it is not only scientists who listen. Engineers and astronomers see in this silence a future observatory beyond imagination. The lunar far side is the quietest radio environment in the inner solar system, a place utterly shielded from Earth's electromagnetic noise. Here no cell tower hums, no satellite chatters, no thunder of civilization disturbs the frequencies older than starlight. Plans already circulate for a low-frequency radio telescope spread across the craters near the South Pole, its antennas unfurled like silver vines in eternal night. Such an instrument could hear cosmic whispers from the dark ages of the universe, the era before the first stars were born, when hydrogen clouds absorbed and re-emitted the primordial radiation of creation. From that distant hum, we might learn how the first galaxies kindled light. Imagine walking there beneath a black sky unpolluted by glow. The ground crunches with glass dust finer than ash. Above the jagged horizon, the Milky Way arches brighter than any telescope image. Earth is absent, its blue heartbeat hidden forever. Each step echoes in your suit, not in the air. Sound travels only through your bones. In the distance, perhaps a future array of dish-like petals waits, catching signals that have travelled 13 billion years to arrive. The far side is not just absence, it is presence of a different kind. It preserves what noise elsewhere has drowned. The craters hold the record of every blow since the beginning. The regolith seals the chemistry of early magma. The silence keeps open a window to the cosmos itself. It is a museum without walls, a cathedral without sound. The moon's two faces, once symbols of mystery and revelation, now feel like complementary halves of a single idea, one lit by our reflection, the other lit by time. The near side mirrors us, our tides, our nights, our stories. The far side remembers what came before us and what will outlast us. And so the exploration continues, robotic scouts crawling in the dust lasers, pinging from orbit engineers sketching the next observatories in the dark. Every new mission extends a human sense deeper into that silence. It is not conquest, but communion, a careful listening. In the next part, we return from the far side stillness to the moving bond itself, to the ongoing pulse between Earth and Moon. We'll trace the faint but constant forces that still bind the two, a reminder that even across silence, the conversation of gravity never ends. If you stand on any coast at twilight watching the tide creep up the sand, feeling that long, slow breath of the sea, you're witnessing the oldest machine on Earth still running. Each rise and fall of water is gravity translated into motion, a reminder that the bond between Earth and Moon is not a memory, but a living system. The Moon still pulls, the Earth still answers. The conversation continues patient and unbroken. Even now, the same tidal forces that once slowed the Moon are reshaping both worlds. The friction of ocean against seafloor of water against rock transforms rotational energy into heat. It's quiet but colossal, an estimated 3.7 terawatts of power, nearly the equivalent of all human energy use dissipated constantly as thermal turbulence in the oceans. Every wave that breaks is a spark of that conversion, a ripple of energy turned from spin to warmth. This process is the heartbeat of a living equilibrium. The Earth's rotation still drives tides slightly ahead of the Moon's orbit, giving the Moon a gentle push outward. In response, Earth's day lengthens by roughly 1.7 milliseconds per century, an imperceptible slowing, but measurable with atomic clocks and laser reflectors. Meanwhile, the Moon continues to recede at 3.8 centimeters per year, its orbit widening like a slow exhale. What seems static to us is a system constantly tuning itself, exchanging energy until both find harmony. We can see the marks of this rhythm written into Earth's deep past. In cliffs of tidal rhythmites, thin alternating layers of sand and silt, preserved in ancient seabeds, scientists have counted the echoes of tides from 500 million years ago. Each couplet of layers represents one lunar cycle, and the spacing between them records the interplay of daily tides and monthly orbits. The numbers tell a clear story. Around 620 million years ago, there were about 400 days in a year, and days lasted only 21 hours. The Moon then was about 20,000 kilometers closer than it is today. Those sedimentary rocks are the Earth's diary entries, proof that the gravitational dialogue has been running far longer than life on land. The Gulf of Carpentaria in Australia, the Bay of Fundy in Canada, and the broad continental shelves of the North Sea all act as amplifiers of this ancient exchange. Their tides rise and fall with enormous power, hundreds of cubic kilometers of water, moving twice a day, their motion slightly out of step with the Moon's position. In that tiny lag lies the friction that fuels the whole mechanism. Instruments placed in the deep ocean now track that transfer in real time. Satellite missions like TOPEX YASA Poseidon and Jason 3 map the sea surface to centimeter precision, measuring tidal phase, shifts that confirm the gradual breaking of Earth's rotation. The precision is breathtaking, even the subtle delay between tide and moonrise appears in the data. It is astonishing to think that something as intangible as gravity can heat the oceans, shape continents, and alter the length of a day. Yet that's the quiet artistry of the system. The energy lost to friction warms Earth's seas by micro-degrees, but accumulates over eons into climate stability. The Moon's pull stirs ocean layers, redistributing nutrients and regulating currents. Without it, much of the planet's coastal life would wither. Without the Moon's restraint, Earth's spin might wander chaotically, tilting and retilting through climatic extremes. This is not a frozen balance, it's a dynamic harmony, always adjusting, always alive. Think of it like a duet in which both musicians listen closely to each other, adjusting their tempo ever so slightly. The Moon's orbit elongates, Earth's day stretches. As long as friction persists, the tempo keeps changing, but the music remains coherent. The physics of this coupling are simple to write and difficult to feel. The torque generated by the Moon's gravity, combined with the viscous response of Earth's oceans, produces an exchange of angular momentum described by equations stretching back to Laplace and Darwin, George, not Charles. Yet the effect can be sensed with nothing more than bare feet on wet sand. The tide's retreat leaves lines that mirror the curvature of orbit. Its return carries the rhythm of a month 1 billion repetitions old. Even solid rock bears this record. Fossil coral rings from the Devonian period 400 million years ago show growth patterns consistent with shorter days. Each ring marks a sunrise, each cluster of rings a lunar cycle. In the stone skeletons of creatures long gone, you can still count the beats of the gravitational pulse. This ongoing exchange of energy is not loss, but maintenance. The system dissipates heat to remain stable, like a heart releasing pressure with each beat. Physicists describe it as the system's dissipative equilibrium, a state in which motion continues only because energy flows through it. Without that flow, the tides would stop, the Moon would stall, and both would freeze into perfect lock too soon. It is the waste, the friction, the imperfection that keeps them alive. NASA's laser ranging experiments continue to track the drift with millimeter precision. Each night, a pulse of light leaves a telescope in New Mexico or France, strikes a retroreflector left by Apollo astronauts, and returns 2.5 seconds later. Each pulse confirms the distance has grown. The measurements are so consistent that they've become a new yardstick for testing Einstein's general relativity, the curvature of space confirmed by the soft pull of our own tides. Perhaps the most poetic truth of all is that the same force that once tore the moon from Earth now holds the two in quiet embrace, each shaping the other's destiny. Their interaction is no longer violent but meditative. The system has aged into balance, neither at rest nor in struggle, but in a continuous slow dance that sustains both. Stand again at the water's edge and watch the tide draw away. What you're seeing is not just the ocean's breath, but a message sent to the moon. In a few days, the moon will reply with its own tiny step outward. Over millennia, this dialogue has sculpted coastlines, guided migration, and measured the rhythm of time. Energy leaves the system, but order remains. Loss becomes stability. This is the paradox of gravity. It binds by letting go. In the next part, we'll explore how deeply this exchange has shaped Earth's story, how the long conversation between rotation and orbit influenced our climate, our life, and perhaps even our sense of time itself. If you could compress the last 4 billion years into a single symphony, the rhythm of the tides would be its quiet percussion, steady, patient, almost imperceptible, yet essential to the melody of life. Every crash of surf against rock, every retreat of water through sand has been part of a dialogue older than continents. It's a long conversation between Earth and Moon, carried out not in words but in motion. Physics calls it the exchange of angular momentum, but it feels more like a heartbeat. The Moon tugs on Earth's oceans. Earth's faster rotation drags the bulge of water slightly ahead. That offset acts like a lever pulling the Moon forward in its orbit, giving it energy and sending it gradually outward. In return, Earth slows. The cycle is precise, mathematical, and yet viewed from the shore, it feels almost personal, as if the sea itself were breathing in time with the heavens. This slow trade of spin for distance has shaped the world we know. As Earth's rotation eased and days lengthened, the planet's climate grew calmer. Shorter days once meant faster winds, more extreme weather, a more violent atmosphere. Over eons, as the Moon's drag gentled our spin, atmospheric circulation settled, seasons stabilized, and oceans could begin their rhythmic exchange of heat. The tides became a planetary metronome, regulating energy flow between equator and pole, between sea and sky. Without that lunar hand on the wheel, Earth might have been a restless planet, its axis wobbling chaotically, poles, swinging wild climates lurching between fire and ice. The Moon's gravitational anchor keeps our tilt steady at about 23.5 degrees, allowing predictable seasons and long-term ecological continuity. NASA scientists describe this as axial stabilization, but in human terms it is something more intimate, the difference between chaos and home. The Moon keeps time not only for our days and nights, but for the balance of our biosphere, and within that rhythm life found its first foothold. Long before vertebrates walked the land, before lungs drew breath, there were the tidal flats, broad shimmering plains of mud and salt water where the ocean's edge advanced and retreated each day. Each tide stranded microscopic algae, cyanobacteria, and simple multicellular organisms. When the water returned, it fed them. When it left, it forced them to adapt. Over countless generations, these organisms learned to endure cycles of wet and dry, to cling, to crawl, to breathe air. Fossilized stromatolites and tidal laminae in Australia and Namibia still preserve those early experiments in adaptation, wrinkled layers of sediment shaped by organisms dancing to the pull of the Moon. It's no coincidence that the earliest animal tracks appear in tidal sediments. The ebb and flow of the sea created both challenge and opportunity, a daily test that forged resilience. Scientists studying Earth's first ecosystems often speak of tidal forcing the gravitational tempo that shaped not only the planet's surface but life's rhythms. Even our circadian cycles, the internal clocks that govern sleep and wake, may carry echoes of those ancient tides. The 24-hour rhythm of our biology once matched the spin of a faster Earth, and as the planet slowed, life adjusted evolving clocks that stretch and contract to stay in sync with the turning world. In this sense, every living thing is a metronome of cosmic history. Your heartbeat, your breath, your sleep, all tuned by biology's long memory to the tempo gravity set. We carry the moon's influence not just in poetry, but in physiology. The physics behind it all is both simple and profound. Angular momentum must be conserved. Energy must flow somewhere. So as Earth's spin energy diminishes, it feeds the moon's orbit, raising it higher and slowing both worlds toward equilibrium. That energy transfer is seamless, no sparks, no friction visible to the eye, yet its consequences ripple through the ages. It is an invisible economy where nothing is wasted, only exchanged, and like any conversation that endures, it changes tone over time. In the Archean era, the tides may have risen hundreds of meters. Now they rarely exceed a few. The amplitude has softened, but the meaning remains. Each wave that laps ashore is the latest sentence in a story begun when the oceans themselves were young. Imagine the tides as breath inhale, exhale, a planetary respiration tied to the moon's orbit. On average, the ocean's total mass shifts horizontally by billions of tons every day, sloshing from one hemisphere to the other. The sound of surf is simply the sound of gravity meeting time. To the scientist, it's the exchange of energy between coupled oscillators. To the poet, it's dialogue between worlds. And to life itself, it's a rhythm to build upon. Even today, tidal ecosystems, estuaries, mangroves, salt marshes remain the richest cradles of biodiversity on Earth. They pulse with the same rhythm that once shaped their ancestors' cells. The moon may seem far away, but its pull still decides where species feed, migrate and spawn. We often look up at the moon and think of distance of separation, but the truth is the opposite. Every ripple that touches the shore is its touch upon us. Every rotation of our planet is measured against its orbit. The two worlds, though, divided by space, remain entwined in motion, exchanging angular momentum like conversation between old friends who need no words. In that exchange, both lose energy, and both gain endurance. Earth slows, but it stabilizes. The moon drifts away, but it finds serenity. Together they approach a quiet equilibrium that might one day still them both. When that day comes, if the tides cease and the oceans rest, the silence will not mean the dialogue has ended. It will mean the sentence is complete. Until then, each tide is a syllable in the language of gravity, soft, eternal, and endlessly repeating. In the next part, we'll step beyond the shore and look back through the aeons to the time before this balance existed, when chaos ruled and the first sparks of order emerged from violence. The question is not only how the moon learned to be still, but how Earth learned to listen. What if one night the rhythm broke? What if the silence between Earth and moon, billions of years old, was suddenly interrupted by motion? Imagine looking up and seeing the familiar face of the moon rotate. Slowly, impossibly, it begins to turn, revealing a side no human has ever seen in the sky. For the first time in all of human history, the moon would rise with a different face each night. It sounds like science fiction, but it's a question scientists have modelled. What would happen if the moon's tidal lock broke? To undo that lock would take a colossal event, an asteroid strike tens of kilometers wide, or a deep internal shift redistributing the moon's mass. Either could inject angular momentum into its rotation, spinning it faster. The physics are simple, the consequences are not. Within days, the delicate equilibrium that governs our tides and climate would begin to unravel. The gravitational tug that now keeps the moon perfectly oriented would become erratic. The ocean bulges that follow its position would shift unpredictably, rising hours early or late, growing stronger in some regions and weaker in others. Coastlines built on regular rhythm would drown or dry without warning. In a matter of months, shorelines would be redrawn, estuaries flooded, and the pulse of the sea, the metronome of life, thrown into chaos. Tides are not just waves, they are planetary breath. Their timing drives the mixing of ocean layers, the distribution of heat, and the flow of nutrients. With that timing disrupted, entire ecosystems would collapse. Coral reefs and tidal nurseries evolved in harmony, with a consistent lunar cycle. Without it, spawning seasons would fail. Migratory species guided by the moon's light, turtles, fishbirds, would lose their compass. Even humans whose circadian rhythms subtly respond to lunar brightness might feel the dissonance. But the moon itself would suffer far more. Over billions of years it has cooled and solidified into balance. A sudden change in spin would tear at its crust, generating internal stress, where none has existed for eons. The solid rock would flex like old bone. Moonquakes, once mild tremors recorded by Apollo seismometers, would multiply into global convulsions. Cracks would reopen along ancient fault lines. Loose regolith would cascade down crater walls like slow avalanches of dust. From orbit, new landslides would appear as streaks of pale grey visible scars of a body that had forgotten how to move. Inside, the friction of new rotation would heat the mantle. Pockets of partially molten rock quiet for billions of years might stir again. The moon could even vent gases from old lava tubes, painting faint hazes into the vacuum. For a brief time, it might almost breathe again. Meanwhile, Earth would begin to wobble. The moon's gravitational stabilizer, the anchor holding our axial tilt steady at 23.5°, would weaken. Freed from that grip, Earth's axis could begin to wander, perhaps only by fractions of a degree at first, but enough to shift weather patterns and alter sunlight across latitudes. Climate models suggest that without the moon's steadying influence, our tilt could vary chaotically between 10° and 45° over millions of years. Ice caps would grow and melt unpredictably, deserts would bloom, then freeze, seasons would lose their rhythm. Humanity dependent on stable climate would feel the change not as a distant anomaly, but as a global upheaval. The night sky would become unrecognizable. With the moon spinning freely, its phases would no longer follow the calm cycle of 29.5 days. One evening, a cratered crescent might hang where the man in the moon once smiled. The next, an unfamiliar plane would glow. Full moons might brighten and fade unpredictably as the reflective Maria turned in and out of view. Eclipses would become rare, distorted, their geometry broken. Sailors' calendars, ancient rituals, and centuries of navigation all would lose their anchor. There would also be tidal energy unleashed. Earth's oceans, struggling to find a new rhythm, would experience surges as gravitational forces fluctuated. The difference between high and low tides could double in amplitude along some coasts, carving new inlets and eroding entire shorelines. Cities built near sea level, Shanghai, New York, Mumbai, might watch the ocean rise and fall like a restless lung. All this from a moon only slightly out of sync. For a complete break-in lock, the effects would stretch over geological timescales, but even a minor acceleration could cascade into instability. Astronomers at NASA's Ames Research Center describe this scenario as gravitational turbulence, a phase where the mutual torque between two bodies oscillates violently before settling into a new state. It is a dance gone wrong, but physics ensures that given enough time it would find rhythm again. For nature, chaos is temporary. The same tidal friction that slowed the moon once would slow it again. Energy would dissipate, spin would bleed away, and after millions of years the moon would re-enter lock, perhaps with a slightly different face turned toward us. Gravity always seeks calm. Yet the thought lingers, for those million years of disorder, what would Earth look like? Maybe the poles would wander. Maybe ice sheets would sweep across continents. Perhaps humanity would adapt to a world with unpredictable seasons and erratic tides, rebuilding calendars, and faith around the moon's new movement. Our species has always measured time by its light. If that light began to change, our sense of time itself might change with it. To witness the moon spinning again would be both terrible and magnificent, a cosmic reminder of how fragile stability is and how much of our world depends on the balance we take for granted. The moon's stillness is not weakness, it is mastery, the final form of motion refined by time. If that stillness ever broke, the sky would become a mirror of what Earth once was young, unsteady and wild. But given enough centuries, the tides would calm again, the talkie would fade, and gravity, indifferent patient, would close the circle once more. Because in the end, every disturbance in the cosmos seeks the same resolution: stillness through balance, motion through surrender. And perhaps that is why the moon does not spin anymore. It has already learned the lesson every world must learn. In the next part, we return to reality, to the subtle signs that the moon, though seemingly frozen, still moves in ways almost invisible. A lock is never absolute. Even stillness has its breath. The moon's stillness is not the end of motion, only half the story. The other half is happening here beneath our feet in the slow turning of our own planet. We don't feel it, but Earth too is being braked gently and inexorably by the same invisible hand that stilled the moon long ago. Gravity never stops pulling. Friction never stops whispering. Each tide that swells and falls rubs ever so slightly against the ocean floor, converting Earth's spin into heat, the same cosmic exchange that once froze the moon's rotation. It's happening now in real time. The rotation of our world is slowing. The day lengthens by fractions of a second every century, imperceptible to our senses yet measurable by the precision of atomic clocks. Every sunrise lasts a breath longer than the one before. This process has a destination. Astronomers call it mutual tidal, locking the moment when both Earth and Moon turn in perfect synchrony, each showing only one face to the other. When that time comes, a day on Earth will last as long as a lunar month does now, about 47 current Earth days. One hemisphere of the planet will always see the moon hanging motionless in the same patch of sky, while the other half will never see it again. The oceans will stop their eternal migration. The tides will sleep. The physics are as elegant as they are relentless. Conservation of angular momentum demands equilibrium. As Earth's rotation slows, the moon's orbit drifts outward to compensate. But this can't go on forever. The gravitational torque weakens with distance, until one day, perhaps 50 billion years from now, the system finds balance. The torque ceases. Energy exchange stops. The Earth and Moon face each other eternally locked in a duet too slow for life to notice, too perfect to disturb. By then, of course, the Sun will have changed everything. In roughly 5 billion years, it will swell into a red giant, perhaps engulfing Mercury and Venus, possibly even Earth itself. If our planet survives, it will orbit farther out at seas, boiling away its atmosphere stripped. The mutual lock may never fully arrive, but in the cold mathematics of time, the trajectory is certain. The dance is slowing. Whether we are here to see it or not, the Earth is learning the same rhythm that the Moon has already mastered: stillness as balance, rest as completion. This slowing is not decay, but transformation. Physicists describe it in the language of entropy, the tendency of systems to move toward uniformity, to trade motion for order, difference for equilibrium. Over immense timescales, the universe itself is drifting toward that same quiet galaxies, expanding stars, fading energy spreading thin. Earth's tidal breaking is a small echo of that grand story. Every fraction of a second added to the length of our day is another grain of time falling into the universal hourglass. We can almost think of it as the planet's heartbeat slowing with age. When it was young, Earth spun fast, its days only 6 hours long, its surface wild with storms and molten seas. The Moon closer then was a massive companion in the sky, its pull violent and raw. Over billions of years, both have aged together, their orbits smoothing their motions, calming. The Moon has already fallen asleep. Earth is only beginning to drowse. It's strange to think that one day the rotation that defines our sense of time, morning, noon, night, will stop changing relative to the Moon. The clock we built our world upon will have run down, yet even in that stillness there will be continuity. The locked Earth-Moon pair will keep orbiting the Sun as a single joined world, a cosmic couple turning through eternity, balanced by loss, sustained by silence. Some astrophysicists have described this far future state as dynamic rest. Everything moves but nothing changes. The energy exchanges that once drove tides, weather, and even life will have faded into near zero. To a distant observer it might look serene, a pale blue world and its grey companion orbiting in quiet harmony, the ultimate resolution of billions of years of gravitational dialogue. But to us bound by short lives and quick perceptions, it feels melancholy. We think of motion as life and stillness as its end. Yet the universe seems to prefer the opposite. It builds through turbulence and completes through calm. The Moon's stillness, Earth's gradual slowing, the fading of stellar fires, all are expressions of a single tendency toward equilibrium, a soft settling of cosmic dust. If you could speed up time, watch the continents shift, the oceans drain, the sun expand, and the Earth's spin crawl to a halt, it would look like a planet going to sleep. Not dying, but dreaming. The final sleep of motion fulfilled. And maybe that is the deeper rhythm gravity has been writing all along, not endless movement, but a graceful slowing, a return to balance. The tides that once roared will rest. The Moon that once drifted will pause. The Earth that once spun so wildly will finally find peace. In that far-off age, when one face of Earth forever gazes upon the same face of the Moon, the two worlds will share the same long night. Their light will fall together into the quiet sea of space, a final exhale of energy, a slow heartbeat fading into the background hum of the cosmos. And perhaps that is what the universe has been teaching all along, that even motion in the end dreams of stillness. In the next part, we'll look beyond this quiet destiny to ask what that slowing reveals about the nature of time itself, and why, in the vast unfolding of the universe, stillness may be the truest measure of eternity. Though it seems motionless, the Moon is never truly still. Look long enough and its silence begins to waver. Craters on the rim appear to drift in and out of view. The familiar face subtly rocks as though adjusting its gaze. This is libration, the moon's quiet secret. Its small confession that no lock is ever perfect. Even in stillness it moves. To the naked eye, the moon seems forever turned toward us, presenting the same features, mar imbrium, marum tranquillitatis, the bright oval of Tycho near the south. Yet, if you study its edges over weeks, you'll notice something extraordinary. More than half of its surface becomes visible from Earth. In fact, we can see about 59% of the moon's terrain in total, thanks to gentle oscillations that make it sway slightly side to side and nod up and down. These are the moon's secret motions, its quiet breathing in space. There are three main kinds of libration, each born from a different imperfection in the cosmic dance. Libration in longitude is the side-to-side rocking caused by the moon's elliptical orbit. Because its speed changes slightly as it moves closer or farther from Earth, but its rotation stays constant, the moon alternately gets ahead of or falls behind its spin. The effect is subtle, a slow oscillation of about 7 to 8 degrees each way, but enough to reveal terrain near the eastern and western limbs. Over a lunar month, craters like Grimaldi and Mare Crisium seem to peak around the edges, then retreat again. It's as if the moon were leaning forward to listen, then drawing back into its stillness. Libration in latitude tilts the moon north and south by roughly 6.5 degrees. This happens because the moon's rotational axis is inclined slightly about 6.7 degrees to the plane of its orbit around Earth. As it travels along that tilted path, we alternately glimpse over its north pole, then its south. The result is a subtle nodding motion, a lunar yes in slow time. Across the span of a month, the polar regions come and go, inviting and withdrawing like breath. The third type, diurnal libration, is the smallest yet most personal. It arises not from the moon's orbit, but from ours, because we observe from different points on Earth's surface as the planet turns our vantage shifts by roughly 1 Earth radius, about 6,400 kilometers, changing the angle by just over 1 degree. It's a daily pulse, a gentle parallax that adds to the illusion of the moon's motion. In this way, even our own rotation becomes part of its rhythm. Taken together, these librations let us see around the edges of the moon by nearly 1/10 of its circumference. The borderlands revealed by this motion are strange and alluring cratered horizons, half in light, half in darkness. For early astronomers sketching the moon through telescopes, these shifting boundaries were proof of its subtle vitality. Galileo himself noted the effect without knowing its name. Later observers like Riccioli and Hevelius charted features that seemed to appear and vanish, puzzled by a world that refused to stay still. Today, spacecraft record these motions with exquisite precision. The Lunar Reconnaissance Orbiter, LRO, circling since 2009, measures changes in the moon's surface height to within centimeters using its laser altimeter. Over time, its data reveal how the moon's orientation wobbles with each orbit, tiny shifts consistent with models of gravitational interaction and interior structure. These observations even hint at the liquid core beneath the crust, roughly 350 kilometers wide, sloshing slightly, as the solid mantle oscillates above it. The moon's rocking is not just surface motion, it's the expression of an interior still cooling, still adjusting, still alive in slow physics. Laser ranging from Earth confirms the same story. Each time a pulse of light hits an Apollo retroreflector and returns, the exact timing betrays the moon's orientation to within millimeters. Those data form a chronicle of the moon's subtle heartbeat, its axis drifting its center of mass offset its dance around equilibrium continuing through centuries. From these records, scientists have even inferred that the moon's core mantle boundary is molten, allowing a slight decoupling like a dancer's body moving independently from her feet. There's poetry in the numbers. Though the moon's rotation is locked, its soul is restless. Its body sways with invisible tides flexed by Earth's gravity and the inertia of its own layered interior. Each oscillation releases a whisper of heat, a quiet echo of the ancient friction that once slowed it down. If the moon were a bell, these librations would be its lingering ring, a vibration that never fully fades. To imagine it, visually picture the moon floating in the dark sea of space, tethered by gravity's invisible string. It rocks minutely side to side, forward and back its surface, glinting alternately in sunlight and shadow. Over weeks, its features seem to breathe, expanding and contracting in our view, like lungs drawing in cosmic air. The illusion of stillness gives way to a realization even equilibrium has motion, even silence has pulse. In these subtle gestures, the moon reminds us that rest is never absolute. It is a dynamic balance, an oscillation too slow for the senses but vital to the system. The moon may appear frozen, but its every rock and nod tells a story of tension, seeking calm, a story as old as gravity itself. And so, the next time you look up at that familiar face, remember that it is not fixed. It leans toward you, then away, bowing gently in an endless act of grace. It breathes. In the next part, we'll explore the mirror of that motion within the moon's inner life, its molten core, its tremors, and the residual warmth that still flows beneath its frozen crust. Because even in stillness, worlds can keep a hidden fire. For centuries, the moon seemed the very emblem of silence, grey, airless still. But now we know that within its quiet geometry lies rhythm, a subtle, mathematical music conducted by gravity itself. Every wobble, every sway, every fractional tilt of libration is part of a symphony so precise that scientists can read its notes to learn what lies beneath the surface. The key to that melody is precision. Modern instruments, NASA's Lunar Reconnaissance, Orbiter, the Grail mission and Earth-based laser ranging have recorded the moon's motion to within millimeters. Those tiny deviations, when charted over years, reveal that the moon is not perfectly rigid, but slightly elastic, flexing with the pull of Earth's tides. That flexure imperceptible to the eye is how we discovered that the moon still harbors warmth and movement within. Data from GRAIL, the Gravity Recovery and Interior Laboratory mission, 2011-2012, mapped the moon's gravitational field with exquisite clarity. Two twin spacecraft chasing one another in orbit measured their mutual distance with microwaves. Each time they passed over a denser region of crust, their spacing changed by fractions of a micron. From those variations, scientists constructed a gravity map of breathtaking detail revealing buried concentrations of mass called mascons, mass concentrations, beneath giant impact basins like Imbrium, Serenitatis, and Crisium. These mascons are the frozen scars of colossal collisions filled with dense basaltic lava. They tug imperceptibly on the orbiting spacecraft and on the moon's rotation itself, producing slight imbalances that feed into the pattern of libration. When the data were combined with seismic records from the Apollo missions, a portrait of the moon's interior began to emerge. Beneath the crust lies a mantle of partly crystalline rock, and below that a liquid outer core about 330-350 kilometers wide, encasing a small solid inner core roughly 240 kilometers across. Between them, molten metal flows, slowly iron mixed with sulfur and nickel, creating a faint magnetic field, the fading echo of a once active dynamo. The librations act like a natural seismograph sensitive to the slightest slip or oscillation. When NASA modeled the moon's motion using this data, they found that the amplitude of its wobble could not be explained by a fully solid body. Only a liquid layer inside could allow such independent movement. In essence, the moon's gentle nodding betrays a heartbeat, still faintly beating deep within a slow pulse of molten motion, under a crust that seems dead. Even the mascons contribute to the rhythm. These gravitational knots cause tiny irregularities in the moon's spin rate microvariations that LRO's laser altimeter has measured over time. The moon therefore doesn't rotate like a rigid clock, but like a living pendulum swaying slightly around equilibrium. It's a celestial rhythm that never stops torque from Earth, pulls internal structure, yields, and then returns over and over again. The precision of these observations is staggering. A single laser pulse from an Earth observatory reflected off an Apollo retroreflector can measure the distance to the moon to within a few millimeters across 384-400 kilometers of space. When those numbers are plotted, they reveal not a flat line but a waveform, a slow oscillation repeating every month traced in light. The moon's stillness, when seen through this lens, becomes a form of motion so refined it feels biological. It's tempting to think of these vibrations as the music of equilibrium, a harmony between rigidity and freedom, between rest and movement. The moon, perfectly balanced yet never inert, carries in its motions the same paradox found in a heartbeat or a breath's stability maintained through fluctuation. Physicists describe this with the language of resonance and damping. The gravitational coupling between Earth and Moon creates a forced oscillator, a system that vibrates within narrow limits, energy constantly exchanged, but never exhausted. Like the plucked string of a violin, it rings softly endlessly. The sound is inaudible, but the mathematics are music oscillation periods, amplitudes, damping coefficients, each a note in gravity's score. NASA's long-term tracking of the moon's libration now allows scientists to monitor not only its orientation, but its thermal evolution, how quickly it is cooling, and how much liquid remains within. Subtle changes in the pattern of wobble hint at heat slowly bleeding away from the core, perhaps through partially molten channels beneath the south polar basins. Even in its near-frozen state, the moon is not entirely still. It exhales warmth into the dark as if dreaming of its molten youth. To poets and scientists alike, there's something deeply human about this precision. The way a lifeless sphere can move with such grace, the way numbers can reveal heartbeat where none was expected. Through instruments and equations, we have learned that the moon's stillness is an illusion. It lives in balance, its motion contained within invisible limits, its song inaudible but perfectly pitched. If you could translate that libration into sound, if every millimetre of sway became a note, you'd hear a rhythm like a slow tide or a distant lullaby, a whisper of motion held between worlds. And maybe that's what equilibrium truly is, not the absence of change, but the presence of perfect rhythm. In the final part, we'll step back from science and listen to what this rhythm means for us, for the Earth, for the passage of time itself. Because the moon's quiet music isn't just physics, it's the pulse of wonder that has always kept us looking up. It's hard not to wonder why this moon, why this flawless balance, this perfect lock where one world eternally faces another. The odds at first glance seem almost impossibly poetic. The same rotation time, the same orbital period, the same proportion of mass and distance that make the moon hang just so large enough to dominate our sky, small enough to stay. Is this mere coincidence, or something deeper written into the mathematics of nature itself? When we look elsewhere in the solar system, we find other examples of tidal lock, but none with quite the same intimacy. Mercury, for instance, is caught in a 3-2 resonance with the Sun, 3 rotations for every 2 orbits, neither free nor fixed. Pluto and Charon, though, are fully locked to one another, facing forever across the void, like an old couple orbiting in slow waltz. Many of Jupiter's and Saturn's inner moons, Io, Europa, Ganymede, Enceladus, Titan, are tidally locked too, their parent planets filling their skies. Yet none of those systems mirror the eerie symmetry of our Earth and Moon. Part of that is scale. Our Moon is huge relative to its planet, about 1/81 of Earth's mass, far larger in proportion than any other natural satellite in the solar system. Most moons are mere fragments compared to their primaries, but ours is a companion world. The gravitational pull between them is correspondingly strong, ensuring a rapid evolution towards synchronization. Mathematically, it was almost inevitable that such a massive moon orbiting a dense, water-covered planet would find this balance within a few billion years. Nature, it seems, didn't aim for beauty, it simply followed the numbers. And yet the result is beautiful beyond reason. The moon's orbit, its distance, even its apparent size, conspire to produce phenomena that feel almost too precise, total solar eclipses, where the moon covers the sun, exactly neither too small nor too large. The ratio is exquisite. Our moon's diameter is about 400 times smaller than the sun's, but it is also 400 times closer to us. The alignment allows moments of perfect darkness, when day turns briefly to night, and the sun's corona blooms around the lunar rim like a halo. It's a coincidence of geometry, yes, but one that borders on artistry. Scientists call it emergent order structure, arising from chaos, meaning born of math. The laws of gravity, friction and motion are impartial, yet they sculpt worlds that seem to know elegance. The lock between Earth and Moon is not miraculous. It is the natural consequence of tidal evolution written in Newton's calculus. But for us bound to fleeting lifespans, it feels like design because it is so complete. We can trace its inevitability. A massive impact with Theia gave Earth a fast spin and a close companion. The new moon molten and near-raised enormous tides, converting rotational energy into heat. Over eons, that exchange slowed Earth's rotation and pushed the moon outward until their rhythms matched an equilibrium where torque vanished, energy exchange minimized, and time itself seemed to pause. Statistically, such a lock is likely in any system where one body is large, the other close, and friction persistent. In cosmic terms, it is common, but in human terms, where we measure rarity not by frequency but by feeling it is singular. Perhaps that's the essence of wonder, the recognition that inevitability can look like intention, that what physics demands can also feel like poetry. If we were anywhere else, the moon might be too small to hold our gaze, too distant to stir our tides too fast, or too slow to mirror our rotation. But here it is just right, the Goldilocks balance of gravitational coupling. We happen to live in the window of time when this symmetry exists. The moon is still retreating, In the distant future, total eclipses will vanish as its disk shrinks in the sky. We are in a sense privileged witnesses to the exact era when geometry and gravity align to make the sky sublime. Is that coincidence, or simply the universe being generous in its timing? Philosophers might call it the anthropic principle that we notice such harmony precisely because it allows beings like us to exist and marvel. The moon's pull stabilizes Earth's tilt, moderates our climate, and nurtures life that can look upward in curiosity. Without that balance, perhaps we wouldn't be here to ask the question. In that sense, the lock is both coincidence and condition, a necessity of physics that became the stage for consciousness. There is comfort in that thought. The lock was not designed for us, yet it shaped the world that could hold us. The moon's stillness is indifferent, yet it mirrors our search for meaning. When we gaze up at that face, one hemisphere always watching, we see more than rock and shadow. We see the result of billions of years of motion, friction loss and balance, condensed into a single gesture, one world holding another in eternal regard. Maybe coincidence and design are not opposites, but two perspectives on the same harmony, one mathematical, one emotional. Gravity doesn't intend beauty, but it creates it all the same, and so the moon remains there perfectly poised between motion and rest, its silence both inevitable and miraculous. Not proof of design nor absence of it, but evidence that the universe in obeying its own laws can produce moments that feel like art. In the final part, we'll bring this journey full circle to the meaning of stillness itself, and what the moon's eternal gaze teaches us about time loss and the quiet grace of balance. For all its apparent perfection, the moon's lock is not a miracle. It is the slow triumph of physics, the inevitable consequence of motion, meeting resistance energy, meeting time. Every wobble, every slowing tide, every lost rotation was part of a long negotiation between order and chaos. When scientists at NASA's Goddard Space Flight Center and the European Space Agency run simulations of the Earth-Moon system, the result is always the same. Given it enough time, tidal friction leads to synchronization. The models show it unfolding in stages, a planetary ballet choreographed by gravity's patience. First, the moon spun rapidly its days, lasting only a few hours. Earth's tides pulled at it unevenly, raising bulges of molten rock that lagged behind its motion. Those bulges acted like brakes, transferring angular momentum outward and slowing its spin. Over tens of millions of years, the rotation matched the orbit. The lock clicked into place. It didn't happen suddenly. Computer models using data from Grail LRO and high-precision laser ranging suggest the process spanned hundreds of millions of years, modulated by the moon's internal structure, its molten core crustal thickness and mantle viscosity. Each parameter tuned the pace of the dance. Planets and moons everywhere follow the same law. Energy seeks the lowest gradient, motion seeks equilibrium. Tidal locking in this sense is the universe's way of exhaling. The ESA's Smart 1 mission and later analyses by planetary dynamicist Dr. Veronique Dehant describe this as a form of gravitational viscosity. The moon deforms under Earth's pull, and that deformation lags just enough to drain rotation energy. The same principle slows Earth itself and has captured countless other moons in the solar system. Io around Jupiter, Enceladus around Saturn, Charon around Pluto all spin in step with their primaries, each balance achieved through friction's steady grace. The mechanism is universal, the music inevitable. NASA's Jet Propulsion Laboratory describes it even more poetically. Tidal locking is gravity's patience made visible. No sudden symmetry, no divine tuning, just eons of invisible work, talkie after talk, until chaos cools into calm. In this view, the lock is less a miracle than a form of weathering. Just as wind smooths mountains, gravity smooths motion. Systems evolve from turbulence to rhythm, from irregular spin to predictable orbit. What looks like design is simply endurance, the result of enough time for friction to win. The moon's stillness is carved not by intention but by inevitability. In those same simulations, scientists can replay the process from the beginning. A newly formed moon hot from the Theia impact spins wildly, perhaps once every few hours. The tides it raises on Earth are titanic, hundreds of meters high. Each cycle drags on the moon's rotation, producing enormous heat inside it. Over millions of orbits, its crust cools, the bulges shrink and the rotation slows until it matches the orbit exactly. The chaotic becomes harmonic. What began in fire ends in balance. That's the story written everywhere in nature. Gas clouds collapse into stars, stars flatten into disks, dust aggregates into planets. Every phase starts with disorder and ends with pattern. The Moon's lock is simply that same narrative rendered in orbital mechanics, a visible example of entropy-finding structure. The Grail mission confirmed that even the Moon's imperfections, the mascons, the asymmetric crust, played a role in stabilizing the lock. Those dense patches act as internal counterweights, anchoring its orientation and dampening the last traces of free rotation. Without them, the Moon might still oscillate chaotically. Instead, they freeze it in that perfect posture face-to-face with Earth. Chaos literally became foundation. And so when we look up, we are seeing the end product of 4.5 billion years of gravitational patience, a process that required no plan, only time. The cosmos doesn't rush toward perfection. It drifts there. In that drift, friction becomes sculpture, randomness becomes rhythm, and the universe writes poetry and equations. If you speed the simulation forward, the same principle continues. Earth too will slow its days, lengthening its own tides, weakening until both worlds are locked together. The pattern repeats because the law is universal energy must be spent to reach stillness. Perhaps that's the quiet lesson embedded in the Moon's gaze, that order is not born of command but of surrender. What we call harmony is simply motion that has grown patient enough to rest. In the next and final part, we'll close this journey with reflection, with the philosophy behind the physics. The Moon's stillness is not an end, but a mirror showing how time transforms chaos into calm, and why wonder like gravity is what keeps the universe awake. It began not with serenity, but with violence. Before there was a moon, before there was even an Earth, we would recognize the solar system was young and wild, a crowded arena of molten worlds colliding in gravitational chaos. Around 4.5 billion years ago, the newborn Earth spun fast and hot, wrapped in a haze of steam and volcanic gas. And then came the intruder, a protoplanet roughly the size of Mars, now called Theia, named for the Titaness, who in myth was mother of the Moon. In that ancient dawn, Theia crossed paths with Earth in a slow-motion cataclysm. Computer simulations from NASA's Ames Research Center and ESA's Planetary Formation Group show the two bodies colliding at an oblique angle, neither head-on nor glancing, but just enough to mix their fates. The impact released more energy than the detonation of a trillion hydrogen bombs. For a few hours, the solar system had a new sun-Earth itself incandescent. The crust vaporized instantly. Oceans of rock turned to gas. Shock waves rippled through the mantle at tens of kilometers per second, and iron from Theia's core plunged inward, merging with Earth's own. Around the impact site, fragments of molten silicate were hurled into orbit, a glowing halo of debris stretching tens of thousands of kilometers into space. In the vacuum, that fiery shrapnel spread and cooled, forming a disk of vaporized rock encircling the planet. Temperatures exceeded 5,000 degrees. Silicate clouds condensed into droplets. Droplets fused into clumps and clumps into boulders. Within weeks, gravity gathered them into swarms. Within months, into a single growing sphere. The newborn Moon coalesced out of chaos, its outer layers molten, its surface shining with the light of creation's furnace. Simulations published by NASA and ESA in recent decades suggest that much of the debris came from Earth's outer mantle, not from Theia, a fact confirmed by Apollo rock samples which show isotopic fingerprints, nearly identical to terrestrial ones. The Moon, in other words, is Earth's echo, our planet's own matter thrown outward and frozen into orbit. It is both child and mirror. The scene defies imagination. Where the Pacific Ocean now yawns, molten rivers once poured skyward. Plumes of vaporized iron and silicate wrapped the planet in a glowing shroud. As the debris cooled, it rained incandescent droplets back onto the forming Earth rock, rain scientists call it, reheating the surface again and again. For thousands of years, the young Earth glowed red through curtains of smoke. Above it, the Moon orbited close enough to fill half the sky tides hundreds of meters high, tearing at both worlds. But from that destruction came stability. The collision tilted Earth's axis to its familiar 23.5 degree arm, setting the rhythm of our seasons. The Moon's gravity would later steady that tilt, taming the chaos Theia had unleashed. Out of ruin, balance was born. Planetary scientists describe this paradox as destructive creation, the cosmic pattern in which impact breeds order. Without the collision, Earth might have remained a fast-spinning erratic world, with violent seasons and unstable climate. The Moon's formation gave us slower rotation, gentler weather, and eventually the conditions for life. Theia's strike was catastrophe as sculptor. Even now, every rock we find on the Moon carries the fingerprint of that event. The isotopes of oxygen, titanium and tungsten in lunar samples match Earth's mantle almost perfectly, as if the two were siblings separated at birth. Grail's maps of the lunar interior show crustal asymmetries signatures of molten rock sloshing in those first 100 million years after impact. The Moon still remembers the direction of the blow. Its centre of mass remains offset toward us by nearly 2 kilometres, a permanent lean born from collision. For a time, the young Moon glowed like a second sun. Its surface stayed molten for tens of millions of years, a magma ocean shimmering above a half-formed core. Gradually it cooled, crystallized and darkened. The heavy minerals sank, the light ones floated to form the anorthosite highlands that still gleam today. The era of fire ended. The long cooling began. To visualize that transition is to watch chaos becoming geometry, molten arcs collapsing into orbit, glowing vapor condensing into stone, two worlds, separating but never truly apart. Out of the violence that could have destroyed both came the quiet partnership. We know the perfect lock, the long tide, the face that never turns away. Theia's death was the Moon's birth. The collision that nearly unmade Earth instead defined it. The impact reminds us that creation is rarely gentle, that balance often begins in ruin. From that incandescent storm came the conditions for oceans, continents, and eventually eyes capable of looking back in wonder. When we stand beneath the Moon tonight, we are seeing not a stranger but a scar made beautiful, the memory of the day Earth became two. In the next part, we'll follow that memory forward, how the glowing child of Theia cooled, cracked and wrote its autobiography in craters and seas, how the chaos of birth turned into the rhythm of ages. When Apollo astronauts brought home their boxes of grey dust and pale stones, they were unknowingly holding mirrors of Earth's past. In laboratories back on the ground, geochemists began the meticulous work of comparing isotopes, those subtle atomic signatures that tell one world from another. What they found changed the story of our origins forever. Every planet, every meteorite bears its own isotopic accent, a slightly different ratio of oxygen, titanium, tungsten, or silicon that reveals where in the solar nebula it formed. Yet the Moon's samples spoke our own language. The ratios of oxygen 17 to oxygen 18, of titanium 50, even of tungsten 192, were virtually identical to Earth's mantle rocks. No other two bodies in the solar system share such kinship. It was as if the Moon were not another world at all, but a piece of our own planet lifted, burned and cooled into orbit. This finding confirmed what physics had already suspected, that the Moon is a fossil of fire, a remnant of the Theia impact, its material once molten, once airborne, now frozen in exquisite silence. The Moon carries the isotopic memory of that cataclysm, as if the heat of creation left a chemical scar that never faded. Yet new simulations, more sophisticated than ever, suggest that the story may be even stranger. Around 2018, planetary scientists proposed the Synestia model, a vision not of two bodies colliding and separating, but of their total merger into a single vaporized torus of rock and metal. For a brief geologic heartbeat, perhaps only a few hundred years, Earth and Theia became one continuous whirling cloud of molten vapor thousands of kilometers wide. Within that incandescent storm, droplets condensed and fell like rain, forming the Moon from the outer cooler regions of the cloud, while the inner mass recoalesced into Earth. In this model, the Moon was born not around the Earth, but within it out of a shared storm of matter, gravity and flame. It explains the identical isotopic fingerprints. How could they differ if both bodies were once one? The Synestia hypothesis, tested through NASA's and ESA's computer simulations, dissolves the boundary between creation and destruction. It shows how obliteration can briefly produce unity, how the violent unmaking of one planet can give birth to two. The Moon still carries that memory in its internal structure. When NASA's Grail mission mapped the lunar gravitational field with twin orbiters in 2012, it uncovered a world far from uniform. Hidden beneath the crust are vast density anomalies, the mascons of old impact basins, pockets of heavier rock, where the surface once sagged and refilled with molten basalt. They reveal a Moon whose outer skin froze even as its interior continued to churn. These subsurface patterns are echoes of its fiery birth arrested in stone. Grail's data also confirm that the Moon's centre of mass lies almost 2 kilometers closer to Earth than its geometric centre. The impact's asymmetry is still written in its bones. The very lock that now holds it steady is anchored in that uneven distribution of mass. Stillness here is the shape of healed violence. The philosophical symmetry is impossible to ignore. What began as an explosion ended as balance. The same forces that once tore a planet apart now keep two worlds in quiet embrace. The moon's tranquility, its soft light, its unchanging face isn't the absence of catastrophe. It is its resolution. It is the aftermath learning peace. When you look up at the moon, you are seeing the frozen crest of that ancient fire. Every crater, every mare, every grain of dust is a cooled echo of something once incandescent. The lunar highlands are the ashes of vaporized continents. The basalts of the Maria are lava that flowed from deep fissures as the young moon tried to heal its molten wounds. The transition from chaos to calm, from heat to harmony, is not merely geological, it's universal. Every system in nature moves from turbulence toward structure, from explosion toward equilibrium. The moon is that law made visible, a monument to entropy's gentler face. Its stillness is not emptiness. It is remembrance refined into rhythm energy, distilled into form. The moon's unchanging gaze is the silence that follows understanding, the way a scar ceases to hurt once it becomes part of you. The next part will carry that thought home, how this ancient partnership, Earth and Moon impact and healing, shape the possibility of life itself, and why our very existence depends on the calm born from that primordial storm. In the end, Earth and Moon are not master and satellite, but partners, two worlds bound in an ancient equilibrium. What began as impact and aftermath has evolved into balance, a slow duet of gravity and time. Their story is not one of dominance, but of mutual shaping. Each has changed the other in ways too deep to ever undo. When the moon first coalesced from the debris of Thayer's impact, it circled a young feverish Earth at only a fraction of its present distance, perhaps 25,000 kilometers away, close enough that it loomed 50 times larger in the sky. Earth's rotation was furious, then completing a day in just 5 or 6 hours. The gravitational pull between the two was immense. Tides surged hundreds of meters high, dragging across molten shores and transferring spin energy outward. Over billions of years, those tides became the bridge of their dialogue. Each cycle slowed. Earth's spin extended the length of the day and pushed the moon farther into space. Now it drifts at 3.8 centimeters per year, orbiting at an average distance of 384,400 kilometers. The two bodies have settled into a near-perfect resonance. The moon rotates once each orbit, always keeping the same face turned toward us, while Earth's slower rotation continues to yield energy to the partnership. This gradual exchange is what physicists call a gravitationally coupled binary system, two masses locked not by control but by reciprocity. In such systems, angular momentum passes back and forth like conversation, always conserved, never lost. Over immense spans of time, friction smooths the rough edges, and the pair approaches dynamic equilibrium. In the case of Earth and Moon, this coupling is unique. Our moon is far too large proportionally to be considered a mere satellite. It is 1/4 of Earth's diameter and about 1/81 of its mass, large enough to pull not just our tides, but our entire planet's center of mass outward. The Earth-Moon barycenter, the point about which both orbit, lies roughly 4,700 kilometers from Earth's core beneath the surface, but well above the planet's center. Technically speaking, Earth doesn't orbit the moon, and the moon doesn't orbit Earth. They orbit each other, circling a shared point in space. We live in the most literal sense within a binary world. Astronomers sometimes compare this to Pluto and Charon, another gravitationally coupled pair. There, the barycenter lies outside Pluto's surface, making the two bodies true co-orbiters, each forever facing the other in mutual lockstep. Their relationship mirrors our own, though smaller and colder, playing out in the distant twilight of the Kuiper Belt. Earth and Moon are less extreme, but the principle is the same. When two bodies are close enough and massive enough, their fates entwine. Gravity ceases to be a one-way pull and becomes a conversation of equals. What's extraordinary about our pair is how this coupling has shaped not only motion but stability. The moon's steady tug has slowed Earth's rotation into the 24-hour rhythm that governs every life form on the planet. Its gravitational anchor has kept our axial tilt near constant for billions of years, preventing wild climatic swings. In this way, the moon has acted like a cosmic governor, moderating Earth's pace, holding its balance, sustaining its habitability. Without that partnership, the Earth might be a world of chaos, unstable seasons, erratic winds, life forced to adapt to extremes. With it, we have the continuity that allowed evolution's patient work. The equilibrium is not static, but alive, a dynamic balance between motion and restraint. Earth continues to lose rotational energy, the Moon continues its slow drift outward, and both together approach the distant state of mutual lock predicted by orbital mechanics. This will take tens of billions of years long after the Sun has swollen and faded, but the trajectory is clear, two bodies once born of collision aging into symmetry. The system's beauty lies in its imperfection. The orbits are slightly elliptical, the tides asymmetrical, the gravitational field marked by subtle anomalies, the mascons, the offset center of mass, the rhythmic librations that let the Moon breathe. Yet it is these imperfections that make the balance sustainable. A perfectly uniform system would be brittle, a slightly uneven one alive. From space you can see their geometry written in light. The Moon's orbit around the Earth traces a slow ellipse. The Earth, drawn by the Moon's tug, wobbles gently around the barycenter. To an observer beyond, they move as two luminous spheres pirouetting around an invisible point. Their motion is pure orbital choreography, gravity turned to grace. In the vocabulary of science, this is a gravitationally coupled binary. In the language of wonder, it is something even simpler, companionship. The same laws that formed stars and galaxies have written into our sky a story of partnership, the transformation of violence into rhythm, of isolation into harmony. The Earth and Moon are no longer fragments of collision, but halves of a whole. One spins, the other steadies. One shines, the other reflects. Their equilibrium is not perfection, but conversation. Each motion answered, each loss returned. And perhaps that is the quiet truth behind their long relationship, that every balance in the universe is born from tension, that even in orbits and tides, peace is something achieved, not given. In the next part, we'll conclude this odyssey with the meditation that began it, how the Moon's stillness born from chaos continues to shape our sense of time, memory, and meaning. How its silence reminds us that equilibrium is not the absence of motion, but the presence of harmony. Billions of years from now, long after the continents we know have drifted into new configurations, and the seas have reshaped every shore the Earth, and Moon will reach the quiet end of their long conversation. The tides that once roared will still, the orbit will widen no more, and the two bodies will turn together in a single synchronized rhythm, one face to one face bound in perfect balance. Astronomers can model this destiny with confidence. The mathematics are serene. Earth's rotation will continue to slow, the Moon's orbit will continue to drift outward until both motions equalize. A day on Earth by then will last roughly 40% of our current days. The Moon will hang motionless in one hemisphere's sky, an eternal guardian suspended over an ocean that no longer moves. On the far side of Earth, where no moon ever rises, night will be an unbroken permanent stars wheeling with infinite patience. At that point the tidal lock will be mutual. Earth and Moon will orbit their shared center of mass like two dancers, holding an endless pose, each eternally showing the same face to the other. The exchange of angular momentum will be complete. The system will have reached what physicists call tidal equilibrium, where no energy is left to trade, no friction to dissipate. It is the ultimate calm, the final exhale of a 4 billion-year breath. And yet, to us it reads like poetry. The Moon, once born of fire and chaos, will have guided Earth into stillness, a slow tutelage in balance. The seas that once surged under its pull will settle into shallow basins. The daily pulse that shaped life's rhythms will fade, replaced by a timeless hush. Even the planet's axis, so long held steady by the Moon's presence, will cease its slight oscillations. The Earth will no longer wobble, it will rest. In that age, perhaps the Sun will already be changing. Within 5 billion years, it will swell into a red giant, swallowing Mercury and Venus and bathing Earth in searing light. Our oceans may boil away before the mutual lock is complete, but if the Earth survives, if the system endures beyond the Sun's fire, it will drift outward through space, as a binary relic, two cold spheres orbiting in eternal synchrony, turning no faster than the universe cools. Entropy will rule that far future, but not cruelly. What we call heat death is not the end of being, only the fading of difference. Energy spreads, temperature evens, motion relaxes. The same principle that drives galaxies to disperse will drive Earth and Moon to quiet their tides. All things in time seek stillness. All motion is a kind of longing for rest. In the last days of this cosmic duet, an observer, if any existed, might find beauty in the symmetry. The half of Earth facing the Moon will forever see its pale companion fixed in the same place, illuminating a hemisphere that never knows full darkness. The other side will gaze into a perfect night, its stars undimmed, its silence complete. Between them, the line of twilight will no longer move. Dawn and dusk will be permanent opposite edges of a frozen day. This vision of the future isn't tragic. It's peaceful. The long exchange of energy, the friction of tides, and the pull of gravity will have done their work. The Earth will have slowed into grace, the Moon will have drifted into calm, and the system that began in violence will end in serenity. Physicists see this as the natural outcome of thermodynamics. Energy flows downhill, motion evens out, equilibrium reigns. But to us creatures of brief lives and restless motion, it reads like a lullaby. The cosmos, after all, does not die with a bang but with a sigh. Perhaps in that far epoch, the paired worlds will look like a single symbol of balance, drifting through the dark, a glowing dot, and its silver echo turning together in a silence so vast that even time seems to sleep. The Moon's journey from molten storm to frozen harmony will be complete. The Earth's rotation, once furious, will have learned patience. The universe itself, having spent its fire, will settle into stillness, not an end but a rest, not extinction but completion. The dance slows, the tide ceases, the light fades, and what remains is equilibrium, the soft architecture of forever. And perhaps in that final quiet, the Earth and Moon will still face one another as they do now, sharing the same gaze that has lasted across all of history. For even in cosmic sleep, companionship endures. In the final part, we'll close with reflection with the philosophy that has guided this journey, why stillness is not absence but meaning itself, and how the Moon's calm face reminds us that every motion, no matter how fierce, dreams of peace. Far beyond any calendar or measure of history, when continents are dust and memory itself has become a language without listeners, the Earth and Moon will approach the edge of time. What happens next depends not on them but on the fate of the Sun, their creator, their clock, and eventually their undoing. In roughly 5 billion years, the Sun will exhaust the hydrogen in its core. Gravity will crush its center, igniting new fusion in surrounding shells, and the star will expand into a red giant, its radius swelling to nearly 100 times its present size. The inner solar system will become a furnace. Mercury and Venus will melt into the star's body. Mars may drift outward on a new orbit. The question that haunts every model is whether Earth and its Moon will survive that dawn of fire. If they do, they will witness the most sublime catastrophe imaginable. The Sun, now a colossal sphere of dying light, will fill half the sky. Its outer atmosphere, the helium-burning envelope, will reach past Earth's current orbit. The oceans will boil away, the atmosphere will evaporate into plasma, and the rocks themselves will glow dull red. The Moon, once pale and cool, will be bathed in radiance fierce enough to melt its surface anew, becoming a mirror of its own birth. But long before that moment, the pair's gravitational bond will begin to unravel under the Sun's new tides. As the Sun expands, its outer layers lose mass, weakening the star's hold on its planets. The Earth-Moon system will slowly drift outward, conserving angular momentum as the central gravity fades. In some model, this drift saves them the planet, and its companion moved just far enough to escape engulfment. In others, the expanding solar atmosphere, dense with plasma and drag, slows their orbits, drawing them inward to destruction. If survival wins the Earth, and Moon may spend their final days circling a swollen blood-red Sun from a distance of perhaps 200 million kilometers, their surfaces scorched but intact. The tidal lock between them will remain unbroken. One hemisphere of Earth will stare forever into the glowing sky of the dying star. The other will face the Moon's molten shell, lit like an ember. The two faces, one solar, one lunar, will shine across the eternal line of twilight. If destruction wins, the image is even more haunting. As the red giant's outer atmosphere swells and churns, solar tides will grow stronger than the pair's mutual embrace. The Earth's orbit may decay. The Moon's will distort, stretching into instability. For a time, their trajectories will flutter between resonance and ruin. Then, as the Sun's envelope surges past, friction and drag will spiral them inward, the barycenter collapsing toward the heat. The Moon may disintegrate, first torn apart into an incandescent ring. Then the Earth, stripped of its crust, will join the star that once gave it life. Their atoms will merge with the solar wind, drifting outward as vaporized memory. Both fates share one truth: the binary balance cannot last forever. The same laws that forged their harmony ensure its eventual dissolution. Entropy wins, but not maliciously. It simply reclaims what time borrowed. Every orbit ends somewhere. Yet there is beauty, even here at the universe's last horizon. The physics that predict destruction also predict transformation. The sun will shed its outer layers, leaving behind a white dwarf, a pearl of compressed carbon and oxygen, no larger than Earth, shining with the last stored heat of its life. Around it, the surviving fragments of the solar system will continue to orbit in ghostly silence, the scorched shells of planets, the glimmer of asteroids, perhaps the remains of the Earth-Moon pair, dark, airless, tidally fused, circling together through the slight of a star that no longer burns. If any observer were to look upon that scene from a distant galaxy, a faint binary dot around a fading ember, they would see equilibrium in its final form. Not motionless, but eternal in its slowness. Not lifeless, but peaceful in its surrender. This is the last horizon where time itself seems to hesitate. The great cycles of birth and destruction narrow to a single point, energy, diffused, temperature-equalized orbit perfected. What began in fire and spin ends in stillness and light. The Earth and Moon, once a storm of molten stone, will have travelled the full arc of cosmic evolution from collision to companionship to repose. Whether they endure or dissolve, their story will be the same chaos shaped into balance motion, refined into grace, matter returned to the quiet sea of stars. And if silence could speak in that far future, perhaps it would say what the universe has whispered all along, that every light carries its own dusk, and every dusk in the end becomes part of dawn again. In the final part, we close this odyssey with reflection, a meditation on wonder itself, how stillness, balance, and decay are not opposites of life, but its completion, and why the moon's calm face remains the universe's reminder that even endings can be beautiful. Across every scale of existence, from the swirling of galaxies to the vibration of atoms, there is one quiet truth. Energy seeks balance. Motion is not endless. It is a path toward rest. Every orbit, every current, every pulse of light carries within it a tendency to even itself out, to distribute, to soften. The moon's stillness is not unique, it is the visible face of a universal law. The same principle governs the entire cosmos. Stars form when clouds collapse, then burn until pressure and gravity reach equilibrium. Planets cool until heat and motion settle into harmony. Even the vast filaments of galaxies threading the universe are expanding toward balance, their velocities smoothing as space itself stretches. Physics calls this the second law of thermodynamics. Entropy increases gradients, diminish energy spreads. But behind the mathematics lies something almost spiritual, the idea that everything in motion is also on a journey toward calm. This is not death, it is fulfillment. Motion without rest would be meaningless, like a heartbeat that never pauses. The intervals, the still moments, are what give motion its rhythm. Every system in nature breathes expansion and contraction, rotation and slowing life and decay. What we call equilibrium is simply the exhale after creation's long inhale. In the moon story, we can read our own. It began in collision and fire, and through eons of friction and loss, it found peace. Its stillness is not the absence of energy, but the result of energy's long work, the sculpted calm that remains after struggle. Humanity follows the same pattern in smaller scale. We live through our own collisions of desire and doubt, of chaos and meaning, and we too seek an eternal locker balance between movement and rest. Our lives, like planetary orbits, begin with acceleration, childhood, youth, ambition, all rapid motion momentum, gathering without restraint. But time applies its own friction, experience, fatigue, reflection. Gradually our spin slows. What once was restless begins to orbit something steadier, a purpose, a memory, a peace. We learn that equilibrium is not stagnation but wisdom, the ability to hold motion without being moved by it. In meditation in silence, in the rare moments when thought settles, we experience a hint of the same cosmic process, the tidal locking of awareness. The self spinning in its own gravity finds a point of stillness, a face that never turns away from the present moment. That is the human form of equilibrium. From galaxies to minds, the pattern repeats. Order is born of chaos, heat becomes light, motion becomes meaning, and meaning matures into stillness. The moon reminds us that this is not defeat, but destiny. Just as its surface cooled from magma to memory, so do our lives move from turbulence toward coherence. We are each of us fragments of the same thermodynamic story energy finding its way home. If we listen closely, the universe hums with this rhythm. The Milky Way's rotation slows as its stars drift outward. The Sun itself is fading gently as hydrogen fuses into helium and releases its stored potential. Even the heartbeat of a photon, the vibration of an electric field, will one day stretch into the long wavelength of cosmic microwave background. All motion is memory-seeking peace. Perhaps that is what consciousness was born to notice, to look at the moon and see not a distant sphere, but a mirror of our own trajectory from heat to harmony, from striving to rest. Its face tells us that equilibrium is not emptiness, it is completion, the final symmetry between effort and acceptance. So when we speak of stillness of the moon, frozen in its eternal gaze, we are really speaking of time's deepest kindness. Stillness is what remains when everything unnecessary has been spent. It is motion that has learned to listen. And maybe that is why the moon has captivated every culture, every language, every dreamer. It embodies the law that governs all things, the law we feel, but cannot name that everything which moves must one day rest, and in that rest everything finds its meaning. In the final part, we'll let that thought settle into silence, the closing meditation of this journey where science meets gratitude and wonder stands in for words. Because in the end, the moon's stillness is not just an astronomical fact, it is the universe teaching us how to be at peace. Imagine standing on the far side of the moon where no human has yet walked and looking up into a sky that never changes. There is no Earth there, no blue oceans, no drifting clouds, no sunrise or moonrise, because from this hemisphere our planet never appears. The stars hang still sharp and innumerable, unsoftened by air. The silence is so complete it becomes a presence of its own. Even your breath trapped inside a suit would sound like thunder. The landscape stretches to the horizon, pale grey, under the harsh glare of sunlight that lasts for 2 weeks at a time. Shadows fall black as ink. There is no wind to move the dust, no sound to carry the scrape of your boots. Only light and darkness alternating in spans so long they feel eternal. And in that permanent something strange happens to perception. Time slows until it feels almost still. You begin to understand what tidal locking really means, not as data but as experience. The ground beneath you is frozen in a pose billions of years old, tilted forever toward the same direction. On this far side, the idea of day or night is meaningless. There is only illumination and absence. The sun climbs slowly, painfully slowly across the sky, its arc taking nearly a month to complete. Each hour feels like an age. If you were to lie down and look up during the long lunar night, the stars would seem closer than they do on Earth. They don't flicker, there's no atmosphere to distort them. The constellations are steady, crystalline, unblinking. You could trace the spiral of the Milky Way across the black, see the faint red glow of nebulae, and perhaps if your eyes could bear it, sense the steady pulse of the cosmos itself. Here the rhythm of the universe feels more literal. You can almost hear the silence breathing. And yet even on this far side you are not alone. The ground beneath your feet trembles ever so slightly with each distant meteor strike. The moon is constantly whispering through vibrations, tiny quakes, tidal stresses from Earth's gravity on the other side, the memory of impacts recorded in its crust. To instruments, those murmurs are data. To imagination, they are heartbeat and echo the sound of a world remembering. If you could look through the moon, deep into the direction where Earth should be, you'd sense its pull, not visible but gravitational, a constant invisible embrace. It is the unseen companion in this eternal night, tugging gently, imperceptibly, keeping you in place. The Earth's gravity reaches here as a soft thread, an invisible umbilical cord that never breaks. Now picture a second astronaut standing on the near side beneath a motionless Earth hanging in the sky. From their vantage, our planet never sets. It hovers there forever, a blue and white lantern illuminating the grey plains. From their side, time feels different too. Each spin of the stars around that fixed globe marks a month, not a day. They live with the constant presence of home above them, while you on the far side live with its constant absence. Yet both of you orbit together, bound by the same unseen force. Two halves of one whole, separated by distance but united by gravity. It's a metaphor too perfect to ignore. Our perception of stillness or movement depends entirely on where we stand. The moon looks motionless because we rotate together with it. The Earth seems steady from the far side because you cannot see its dance. Even time itself feels slower or faster depending on your horizon. Motion and rest are not opposites, they are perspectives. Standing here you realize how deeply connected stillness and movement really are. Every atom of your body, every grain of dust beneath you vibrates with microscopic motion. Even when you stop, you're still moving, spinning with the moon, orbiting Earth, circling the sun, drifting through the Milky Way. The stillness you feel is only relative, the illusion born from harmony, too perfect to perceive. If you close your eyes, that harmony feels almost human. The same silence that fills this landscape is the one we seek within ourselves, a quiet that is not empty but aware. The moon teaches that awareness by example. It doesn't resist gravity, it listens to it. It doesn't fight motion, it balances it. Imagine leaving a small light burning behind you before departing, a single beacon glowing faintly across the grey dust. In a place where nothing moves, that light would shine unchanged for centuries, perhaps millennia. And though no one might ever see it, its photons would still race outward, crossing space, touching invisible fields, joining the slow conversation between worlds. That is what the moon's stillness reminds us of, that connection doesn't require motion, only presence. The Earth and Moon have faced each other across a gulf of space for billions of years, and in that silence they've said everything that needs to be said. On the far side, beneath an unblinking sky, you begin to understand the cosmos doesn't move quickly or slowly, it simply is. And in that being, in that unbroken stillness, everything that ever was and ever will be continues. In the final part, we'll return to that idea one last time, a closing reflection on wonder itself, and how mystery keeps us awake to the universe's quiet song. For billions of years, the moon has turned in silence, its orbit a perfect memory, its face an unblinking witness to everything Earth has ever been. Empires have risen and vanished beneath its glow, oceans have shifted, forests have burned, and still it remains, tracing its slow path through the dark. To most eyes it looks motionless, eternal. But that stillness is not absence. It is the final shape of motion itself, energy, that has found its balanced gravity, that has learned to rest. Every crater and ridge is a record of movement slowed to perfection. Inside its stones you can feel the pulse of ancient tides, the echoes of molten storms, the friction of worlds learning to coexist. The moon has already lived through everything that could disturb it. Fire impact, rotation and resistance all have been refined into equilibrium. It doesn't stand apart from motion. It embodies the peace that motion becomes when it finally understands itself. In its orbit lies the quiet truth of physics and poetry alike. Nothing lasts forever in chaos, yet everything seeks harmony. The moon shows us the outcome of patience of time, working not as a destroyer, but as a sculptor. The same forces that tore it from Earth's body now hold it steady in the sky, locked in an embrace that has outlasted continents. This is not stillness born of fatigue, it is stillness born of comprehension. Perhaps that's why it feels so calming to watch the moon. Beneath the numbers and equations we sense the philosophy written there, that every motion, if allowed enough time, will find its rhythm, that even the most violent beginnings can mature into balance. The moon is proof that nature heals through gravity, through time, through surrender. When you look up tonight, you're seeing that balance illuminated the glow of a world that has made peace with motion. Its light is the reflection of both struggle and serenity, the radiance of a system that no longer needs to move faster than its own harmony. Science gives us the mechanism, tidal friction, angular momentum, thermodynamic decay. But understanding the process doesn't dissolve the wonder, it deepens it. Knowing how the dance works only makes its quiet beauty more profound. Every photon that leaves the moon's surface travels to us as evidence of that perfection, a beam of equilibrium arriving across a gulf of silence to touch our retinas, our imagination, our sleep. The same laws that govern its stillness govern us. Our hearts beat, our planets spin, our stars burn, all variations of the same eternal process energy, seeking its resting place. To live is to move, to understand is to listen, to rest is to align. The moon simply shows us how to finish the sentence. So tonight, as the world slows and the sky opens, take one last look. The moon will not speak, but it will teach the way silence always does. It reminds us that in the vast, cold machinery of the cosmos, stillness is not an accident. It is the destination written into every motion, the whisper waiting at the end of every sound. And maybe when we finally learn to see that stillness not as emptiness but as meaning, we'll understand what the universe has been telling us all along. Perhaps mystery is how the universe keeps us awake to wonder. Thanks for being here. hit that subscribe button and join us for the next chapters full of history and discovery.